Chers collègues, on reprend. Nous entamons cette dernière séance de la journée avec une présentation de Rainer Blatt, un des pionniers dans le domaine de l'information quantique. Professeur à l'université d'Innsbruck à Autriche et directeur de recherche à l'Institut d'optique quantique et d'information quantique de l'Académie autrichienne des sciences, professeur Blatt est reconnu mondialement pour ses travaux sur les ions piégés et leur application dans les ordinateurs quantiques. Il a notamment cofondé Alpine Quantum Technologies, une entreprise qui développe des ordinateurs quantiques commerciaux. Nous avons maintenant l'honneur d'accueillir le professeur Blatt qui va présenter la manière quantique de faire des calculs, simulations et mesures. À vous la parole.
Good afternoon. Is the microphone on? Oh, perfect. Good afternoon, everybody. My apologies for not speaking French today, but my French is too bad. So I would not be able to deliver this talk fluently in French. So, with my apologies, I would like to start and first by thanking the organizers for having me. It's a wonderful event here, and I'm really happy to be here. And I would like to share with you a little information about what we have been doing over the last years. And the title of the talk, as you can see here, if the pointer works, we'll see that. The pointer does not work. Okay, so sorry for that. Okay, how does the pointer work? Does it work in your screen? Okay, so we do it the old-fashioned way. It does work now? No, it does not. I don't see any pointer.
Should we make the next? What should we?
Just a pointer. Does it work? The next slide? Okay, so let's go back. Let's do it the old-fashioned way. I have my good old-fashioned laser pointer since I'm a laser physicist. So can you see that pointer? Perfect. So see, I would like to share with you some ideas that what we did and some experiments over the last few years in what I call the quantum way of doing computations, simulations, and measurements. And what you will see later on, this is the workhorse. This is our small quantum computer that we are using in Innsbruck to do all these things. What's the menu of today's talk? First of all, this is the celebration of 100 years of quantum mechanics here in Morocco, and I'm proud to be part of that. The International Year of Quantum Science and Technology by the UNESCO has a different motto. It is 100 years of quantum is just the beginning. And we have seen today and yesterday the history of quantum mechanics laid out in detail by Serge Roche and Alain Aspect, and also by Jean Dalibard today. And we want to see where this could possibly be in the next 50 to next 100 years. Personally, I'm convinced that quantum physics is the basis for the technologies of the 21st century. I would try to convince you with that, and we'll see that this is justified to have now the International Year of Quantum Physics. What is the menu of today's talk? I would like to start by sharing with you a few thoughts how computers and technology developed, why we want to have quantum computers in the first place, and then I would like to tell you what are the bits and pieces that we need to make them work. These are quantum bits, quantum registers, quantum gates, and some of the realization concepts. We have heard a little bit about this already today and discussed this. I would like to make you familiar with our workhorse. This is quantum computation with trapped ions. Show you briefly the toolbox, and then we just see what we can do so far. And if there's time, I would like to show you how we have ideas how to scale the system up. So let's get started with a quote of famous people. This is Richard Feynman, but also before that, in March 1949, we have an article in Popular Mechanics that says, the calculator on the ENIAC, this is the Electronic Numerical Integrated Computer at Penn State University in 1947, is equipped with 18,000 vacuum tubes and weighs 30 tons. Computers in the future may have only 1,000 tubes and weigh only 1.5 tons. I would not be here if that would be the case. But think of this, 1986, this is not that long ago, Richard Feynman said we ought to be even more ridiculous later and consider bits written on one atom instead of the present 10 to the 11 atoms. Such nonsense is very entertaining to professors like me. I hope you'll find it interesting and entertaining also, and I want to keep you entertained. So let's start with this. The computer technology, and now I hope that the advancement does work. Somehow this does not work anymore. Oh, now it does. Okay, so progress in technology in computer science is usually measured in terms of the Gordon-Moore's law. Gordon Moore is one of the founding fathers of the Intel Corporation, and he empirically drew the number of transistors that are necessary as a function of the time in the 60s, and this follows a straight line. And then it follows another straight line, which is about 18 months every 18 months the computer power doubles in these numbers. This is not by chance. The reason for that is simply that you have to invent and to have to manufacture the machines that allow you to make things smaller and by this way faster. And this works on and on and on. But the question is there an end to it? Because Gordon Moore already realized no exponential is forever. You can draw the line in a different way. This is data that I took from Rob Keyes from IBM, which were published, and I took the liberty to add it with a few other more modern devices. What we draw here is how many atoms we need in order to realize a single classical bit of information. Of course, these were micrograms in the 60s, but then it goes down to atoms. But if you naively interpret it, already at 2017, this line would cut the single atom line, and it's very clear that even before that, we need to think about the laws of quantum mechanics. Then the question arises, why do we want quantum computers? The generic answer, of course, would be there must be some applications in physics and mathematics. But what are these? In 1994, actually, Peter Shor came up with an idea and with a new algorithm that allowed us and allowed them to factor a large number with L digits. Factoring is one of the hard problems for a classical computer because they have to try it out. There's good sieves and there's good algorithms, but they're not nearly as good as for a quantum computer because the efforts in the length of the digits grow exponentially for a classical computer, whereas on the quantum computer they grow only polynomially. Little later, Love Grover from Lucent came up with an optimization procedure which scales things up by a square root of the numbers. But more importantly, from a physics point of view, is that we now are able to simulate Schrödinger equations and simulate Hamiltonians in a way that we have not been able to do before. We saw some of that already this morning. And also something that has not been mentioned so far is that spectroscopy can be enhanced. I'll show you one example. A quantum computer can be used as an atomic state synthesizer, meaning that if I have a measurement at hand that I really want to do very precisely, I can customize my state by programming a small quantum computer to really be more sensitive with respect to that measurement that we have in mind. And eventually, as a physicist, of course, we have to come up with the idea, and we have to realize now that quantum physics is now viewed in a slightly different way. We look at it with what I call the information-guided eye. I don't have the time to go into this today, but one idea is, of course, that, for instance, the notion of error correction was valid and is still valid, of course, in the classical domain, but it was not supposed to be valid in the quantum domain. In the meantime, we know that it can be done, and quantum error correction is one of the key ingredients that we will need for functioning quantum computers. So there's a large number of reasons to do this. Let's set out and do this. A classical bit, as you all know, is a switch in the up and down position, or a 0 and 1, and the register is just a bit row of these. The generalization to quantum mechanics is simple. It's just a two-level system, or a good old friend, which we depict here in a Bloch sphere or Poincare sphere, depending on what point of view you take. Then the quantum register is just a generalization. You just put L of these numbers, of these atoms by side to present 2 to the L quantum states. But you have to write down the total number quantum state in a different way. You see here is already the direct product between them, meaning that in order to generally write down the state, you have to write the register in a superposition. And that, of course, makes use of the quantum features that we have in the system. That means, in principle, we have a superposition, or more generally, entanglement in this register that can now be used in order to convey the information and to make the decisions. For example, it leads to the following fact. If you had a classical register like that one, and you change the last digit right here, the rest of the digits couldn't care less. But if you change a digit right here, anywhere in between, then everything changes, the entire quantum state changes because of the entanglement that is available in the register. This really means that the procedure, how we calculate, is different. We make use of the wavy nature of quantum mechanics. So instead of just starting from the points where you put the stones in the, say, a lake right here, which form that interference pattern, you also look at the interference pattern and simply say, okay, this is delocalized information. No matter where I look like, I can find out the points where these stones were thrown in. And when you just have another stone somewhere there, then in a delocal fashion, the interference pattern changes at once. And that is again the delocal nature with which you achieve what we call a quantum parallelism. You just change one site and you have a change in the entire pattern. And of course, the computational space is now made by all the interference paths that you have to control. Bear in mind, there's nothing like a free lunch. So if you just add now another qubit, then of course the computational paths grow exponentially, like this on a chessboard. So you have the 64 qubits, that many, that's 10 to the 19 computational paths. In order to get that working, a working quantum computer, you have to control them. That's mind-boggling and daunting, but not impossible. And this is something that we will make use of. Next step is, of course, we have to make a set of universal gate operations. The first thing is a standard rotation of the Bloch sphere. We know this by pointing out the operations on a single atom. We can just tilt the Bloch vector like this. But more importantly, we have to make a so-called equivalence for the Boolean XOR operation, the exclusive OR operation, which we call now a C0 gate operation. You see, this is the truth table. If you forget about the Bra-and-Ket notation of a classical Boolean XOR. But in Bra-and-Ket notation, this hints to the fact that it has to hold for superpositions and not just for the probabilities that you find out there or the state populations. And together, it was shown in the mid-90s, this is already sufficient to build a quantum computer because that's a universal set. That's it. We have a blueprint for a quantum computer. We start out with a superposition. We have a process. That process, of course, is now broken down in a sequence of 2-qubit operations of the C0 case, or single-qubit operations. These phases and the angles may vary. And of course, any sequence of these gates is in an algorithm represented by a programmer that breaks down the task at hand in the sequence. And then we end up with the superposition right here. So far, these are all unitaries, and in principle, I could just revert this and not gain any classical information. But in practice, what we want to do is we want to project this, and then we get one outcome here. So this is, again, as we use in quantum mechanics, it's a statistical feature, and we have to run maybe the computer 2 or 3 times, or maybe 10 times in order to find out what that interference pattern in the register is going to be. Okay, so what are the realization concepts? For the realization concepts, very early on, people have formulated something like a roadmap. That's the US roadmap, which no longer continued, but still has some valuable information. The European roadmap is still continued right here, and if you want to have more information, I would refer you to these popular papers that we've seen already today. This is one by the European Union, the flagship, and the part, and this is from the National Academy of Sciences in the United States. Here I have introduced a bunch of these techniques that have been considered. I will later on talk a little bit about ion traps, but there's also concepts on neutral atoms and traps. We have alluded to that this morning, and the optical traps, optical lattices, microtraps. People also use neutral atoms, cavity QD, NMR, and liquids. Superconducting qubits come in various flavors: charge, flux, phase qubits, solid-state concepts, spin systems, quantum dots, and so forth. There's optical qubits and linear optics, quantum computation, even some exotic ones like electrons on liquid helium surfaces, spectral hole burning, and many more ideas. Out of these, over the last, say, 10 years, of course, these are all systems that can be controlled and manipulated, but over the last years, more and more people have concentrated on these 4 technologies. Others are still investigated, but these are the main platforms that are currently being investigated. I won't have the time to go through all of these. Let me just give you an overview on what we are doing in Innsbruck on the ion traps. The ion trap concept was conceived by these 2 gentlemen. This is Ignacy Sirac and Peter Zoller from Innsbruck. And the idea is simply put the following. We just store the information in individual atoms that are sitting side by side in what we call an ion trap. I'll come back to that in a minute. And the internal degrees of freedom can be used now to store the quantum information. The difficulty was, and there's many other ideas based on that later on by these gentlemen right here, Millman Sørensen, Milburn, Zoguri, and Solano, Johnson, Plénière, Knight, light shift gates, geometric phases, Leibniz and Weinland, and so forth. But the basic idea was to use the common motion of the ions in such a trap to realize exactly that CNOT gate operation. Because the CNOT gate operation is crucial for the operation of such a system. So let's see how this works. Let's start with the qubits. A qubit is a 2-level system which can be realized with hydrogen-like ions, for example. So you take calcium in this case. This is the species that we are using and sort of worked on in Innsbruck for a better part of 30 years. This is a low-lying state, a long-lived state right here. But you find others as well here, and all the ones in blue have been investigated for qubits. The same can be done with lower-lying states in Zeeman states or in hyperfine states, but then in order to address them individually, you really have to use Raman transitions, but otherwise everything is going to be the same, so these are mostly then the odd isotopes right here. I will concentrate on this species. Everything else works in the same fashion right here. You just replace the excitation of the 2-level system by a Raman transition. What are the traps? The traps are derived from what we call a Powell mass filter that was conceived in the 50s, and if you wind rings around this, then you can just keep ions of a specific mass and charge right here in the center, provided you apply the right voltages to these electrodes. There's variants where you replace these rings by these end segments right here, or tips as we have it in Innsbruck. You have also combined or hybrid traps where you have segments and end caps or end plates right here. And the more modern version was invented in Boulder by the group of Dave Weinland. This projects everything on a plane. This is something what we call a segmented planar trap. Now, the trap that we are using for most of the experiments in the early, say, 2000s and until now, although we have others as well, that's a simple trap like this. Is the distance between the tips is about 6 millimeters. The gap width is about 1 millimeter right here. And for the remainder of the talk, you just need to remember this is a harmonic oscillator for ions. A harmonic oscillator is just characterized by the trap frequency, by nothing else. And one single trapped ion right here has a trap frequency along the axis of about 1 megahertz and laterally about 2 megahertz, depending on the voltage that you apply. That's all you need to remember. Now back to the idea of Sirac and Zoller. How does that work? We know now we can encode the quantum bits in these long-lived states, whether in the optical domain or in the ground state Zeeman coherences, and these ions are sitting next to each other right here in the trap. The most important part of that proposal is this state vector of the quantum computer. That state vector simply states the following. Here, I denote all the internal degrees of freedom of the respective 2-level ions, and here is the center of mass motion of the ions. The center of mass motion is just, you know, these ions are repelling each other, this motion that the ions all go back and forth in the trap. Initially, we have cooling these ions so that they are in this ground state, that is the center of mass motion is 0. The ions are stock still, right, standing there in free space. And now the next point is we want to realize that truth table. But how the heck should that ion, which is to be controlled, known know that this ion has an excited state amplitude right here. Now the idea by Sirac and Stoller is the following. We take the excited state amplitude, this is just a number right here, and make an operation, I'll show you how that works in a minute, and move that excitation to a 1. We create one phonon of the motion in the center of mass motion. Once we do that, that single particle of course starts to move according to that one phonon, and since they're all repelling each other due to their charges, then the entire chain starts to move. This, of course, creates entanglement because after a while you just don't know anymore where you put the phonon in. From the point of view of the chain, there's no way of knowing. This is entangling the spin or the two-level system with the motion. Then you just go to that ion and make a transition if and only if there was motion in the system. And finally you go back and take the motion out, and you're left with the truth table as it is indicated here. This requires, of course, individual addressing and efficient single qubit operations of each one here. Small decoherence of the internal and emotional states. You don't want to get things out of sync. And you want the quantum computer as a series of gate operations. So you have to realize that is a sequence of pulses according to what I just said before when you just translate your algorithm into these pulse sequences. And this is how it really looks like. This is the trap as we have it. And these are the trap electrodes, and there's the ions. They are lining up in the center, provided you just shine in laser light in such a way that the ions get optically cooled. In addition, you have here 2 addressing beams that can be moved across the entire chain, so that they just can make single qubit operation, and in the way that they, when you map the motion to the internal degree to the motion, that they also then, of course, create the entanglement. We can always observe the ions in the fluorescence light here in this case, and this is a typical string that we see, a typical register that we have every day. It's not typical in the sense the best we ever observed. We go now up to about 100, but it's really what we observe these days on a regular basis. What are these ions? These ions are calcium. I hinted to that already. And we take now advantage of this low-lying state. The 5/2 state lives about 1 second. So that's our qubit transition. In order to detect things, and we need to detect that with high efficiency, we make use of what's called by Hans Dehmelt the so-called shelving technique. Shelving means the following. When we have a single ion right here, and we shine in laser light to that dipole allowed transition to the P1/2 state right here, then that electron can shuttle back and forth very fast and scatters a lot of light. So when the ground state is occupied, you see a lot of light in the camera that detects the fluorescence light. But once the electron is shelved right here in this state, the electron is not available to shuttle back and forth, so you don't see the light. And we call this, of course, then the spin-up state. This is the spin-down state, the logical 0 and the logical 1 state. And this is how we really then manipulate the quantum state by shining in laser light on the 729 nanometer transition. Detecting things, of course, leads then to the proverbial quantum jump detection that we have seen a long time ago. And this is how we now routinely detect the state with about 99.9 and more percent fidelity, depending on how long you have time to detect things. Okay, so let's summarize things. We have now the 2-level system sitting in the ion trap. That's a harmonic trap. So the numbers of the quantum numbers, we have to write down the Hamiltonian in this way. We have now many of these 2-level systems, which are just different by the trap frequency nu right here, and that energy h bar nu. And so we have many resonance conditions for a laser that we can apply. Applying a laser from the ground state to the excited state with the same n number, of course a carrier transition as we call it, that doesn't change anything except for the internal degree of freedom. But if we tune the laser, for example, to that state, then of course we just subtract one of the phonons right here, and physics tells us that the system now predominantly decays here on this transition, and then it climbs down the entire ladder until it finally resides in the state n equals 0. This is what we call sideband cooling. And then we are left with exactly 3 transitions. It's the ground, the carrier transition, it's the blue sideband that adds a phonon, and the red sideband. And these 3 transitions is exactly what we are using now to realize the entire quantum computation. The carrier manipulates the internal superposition, and the sidebands are used to create the spin motion entanglement, and the details are listed here. And here's the toolbox. The toolbox operations, according to what I just said, are the following. We can make a resonant excitation by shining in the laser along the entire axis, so we all tilt them according to the coordinate system that we have about x or y, about the angle theta. And this typically goes with very high fidelity written here. It takes a few 10 microseconds. For some better excitations, only a few microseconds, depending on what we do. That's a very typical value. But we also can do an off-resonant manipulation, which is often interesting in order to avoid crosstalk in the system. So we don't want to excite that one, but we just make a phase shift here. Then we're using light shifts. Or we can use then the entangling operation, and the entangling operation makes use of the motion of the intermediately excited motion, so it's not exactly the Sirac-Sola idea. That is a gate that was proposed by Møllmer and Sørensen. It works like a two-photon transition. You know, for a good photon transition, then the intermediate states cancel, so it's Doppler-free, and in this case, the motion drops out to first-order approximation, which makes it insensitive to some residual motion. Also, these three blocks give you a universal set of gates with which you can actually really do the entire quantum computation. Now we are ready to do that. For those who are mathematically more inclined and want to know the details, I just give you here the translation table for all these toolbox operations in terms of unitaries. This would be a local Stark effect. This would be a collective Stark effect. This would be a collective local rotation about the angle that is more generally defined right here. And of course, the Møllmer-Sørensen entangling operation can be written down, and keep that in mind, please, as a spin-spin interaction. That's how we do things. But further on, I will only refer to these as blocks and not write down any formulas. In addition to that, we have many more toolbox operations, so we can hide one of the lines, or I can add one line by hiding the population or the state in one of the unused Zeeman states of the system. We have dephasing operations for open system simulations. We have an initialization set. We can do the reset operations, and we even can use two states that are hidden for a full quantum memory, which has a lifetime of, say, a few milliseconds. So this can be done. And now let's go to the lab and just see how these things are really done in life. This is the lab as it is in one of our labs, and this is a typical AMO lab, atomic molecular optical physics lab, lasers and apparatuses. So this is where the ion is hidden somewhere in a magnetic shield. Then there's lots of lasers here. And then we do all of these algorithms. All of them have been done. I will just concentrate on a few examples here and show you how this works for analog, digital, and simulation, and then the quantum metrology part. And if you look in such a lab, typically it looks like this. There's lots of light everywhere and lots of mirrors, and this is awful when you really want to do a computer. No industry is going to buy that. So we sought out in the flagship project of the European Union to really reduce this and to build everything into these 219 Interacts that we have right now. This was done by these two people here, Christian Marciniak and Ivan Pokorelov, and they did a very nice job. And let me just show you now some results on that were now routinely achieved with this tool. I will just show you three simulation approaches. A quantum simulation is usually at hand when you want to have a problem, when you want to compute a problem that is not so easily done on a classical computer. So you take then to a quantum simulator that could be a string of ions, or say atoms in an array, or a superconductor, whatever you do. This is generic. Then we distinguish three different ways of doing these computations. The first one would be an analog simulation. That is to say, we prepare an initial state, and then there is a Hamiltonian that we really want to simulate, and we raise it, of course, exponentially. That means we form the according unitary according to the translation table that I gave you before. And then we apply that unitary for a certain amount of time, and then we just stop here. That is in an analog fashion. We just try out how the system dynamically evolves, see what the population is as a function of time, see all the frequencies, and derive from this how the dynamics of the system behaves. But it requires, clearly, when you just apply this interaction right here, a match between the engineerable interaction and the model that you have at hand, what you want to simulate, which is not so easy often, but can be done, and very successfully done so. In fact, to the extent that today I would say the first really useful quantum computers are those that do analog quantum simulations. A full-blown quantum computation, on the other hand, that we call a digital simulation, is just breaking down the entire process here in a series of unitaries as in a quantum program, the way I showed you before. That quantum program can be naturally done by developing things in a sequence of these unitaries, for instance, by a so-called Trotter-Suzuki approximation, I'll come back to that, or by a programmer who tells you how to break the algorithm down into a sequence. We can discuss this later on, how this is done, and Qiskit is one of the tools. There's Cirq, there's Pennyline, there's many languages and dialects these days, but you can do that. But there's another variant of the simulation which is often overlooked, and that is a combined use of a classical computer and a quantum computer. And what you're doing here is the following. You use a classical computer to hold your problem and do all the tedious calculations like expectation values and whatever. But then you use a quantum simulator, or you just use simply the quantum register. What you do now, the following is that you take the classical computer which has this problem at hand, and the classical computer just says, okay, I want to use a few parameters with which I can optimize my system, and the few parameters give the computer information on what the expected values, the outcomes should be. Then, with these values, you tap into the quantum system right here, you address the system. You don't do the computation in the system, but you just say, okay, I just produce a quantum state that is supposed to behave as I did, as I thought it would do. And then you just make a measurement. For example, you measure the expectation value, feed this back. And once these match, then of course you're done. But often they don't match, then you let the system go and reiterate, and finally you find what you're doing. So this is now also a helpful procedure for simulations. So let's see how we do this. This is the digital approach. As said before, we break down everything in a sequence of unitaries. The difficulty is when you write down the Hamiltonian as a sequence of and parts of these Hamiltonians right here, they do not necessarily commute with each other. So you either take the Hausdorff-Baker-Campbell formula and then write things out, or you take, the unitary in approximation, unitary as an approximative form, and this can be done by the so-called Trotter-Suzuki approximation. That means you replace in that anti-Hamiltonian things piecewise by a unitary, and you apply these unitaries only for a time slice t divided by n. In other words, you just have a full sequence right here, and then you repeat the sequence and repeat the sequence, and the finer these systems are sliced, the better they approximate the unitary that you want to study. That is tedious, and this is why this is not so easy to do. The analog on the approach, on the other hand, for example, shows you how we do it here. The bichromatic excitation, remember, that was the Mermer-Sørensen gate operation. That is tantamount to having, say, dipole-dipole interaction. So you write down the dipole-dipole interaction right here, when you just apply this to the transverse operation, the transverse oscillation right here. And then you detune the system. Detuning is a Stark shift, so we just have that here. And all of a sudden, you see, in this way, you can just write down the entire Hamiltonian as an Ising Hamiltonian. And applying that now with the appropriate detunings and appropriate settings gives you then an analog access to the dynamical behavior of the entire system. And then the interactions can be adjusted, and the details can be found in these reviews. I'll just give you a few examples. Here's a digital simulation that we did more than 12 years ago with 4 qubits. You see here we prepare the spins, and then we see that in a trotterized version how these things work. There are very many qubits, very many gates that we use, and these gates at that time, they were not as good as they are today, and also they were not error corrected. So you see the dark points right here, they run out of steam, whereas the theory tells you that's what you usually would expect. But the dynamics can be learned from this, and you know how the system behaves. And we studied with that many Hamiltonians. We did it, for example, also for a more complicated lattice Hamiltonian here, for a so-called lattice gauge theory, Schwinger model. And this is rewritten Hamiltonian from the theorists. They hand us this down. This comes from the group of Peter Zoller and Christian Muschig, sorry. And then, of course, you have a trotterized version. You apply this 4, 5, 6 times, and then there's more than 200 gate operations, and you get here then the creation of a particle-antiparticle pair as predicted by the Schwinger model. This is in 1D. Today we do these things with more sophisticated programming. Even in 2D, we can make plaquettes and things like that. So this is the physics that we are studying. Then analog simulations, for example, this is again our Ising model that we have studied. This was also studied to see phase transitions here by Chris Monroe and his group. You can see nice the paramagnetic crossover and Néel ordering and the like. These things have been extensively studied over the last 10 years. We did similar things in the case where this B field is much larger, so we just can rewrite that Hamiltonian to flip-flop Hamiltonian right here, and then we see, say, spin excitation and see the dynamical evolution of the magnetization, so that's entanglement spreading. And we see how many body Hamiltonians can behave in such a system. This was also done for transport simulations, so we just see here the ballistic behavior. This is now 15 or 10 ions, whatever, but we can do that also with 20 and 30 ions. And once you now create here this order, for example, by shining in, say, stochastic and randomized Stark shifts on the system, then you created this order. This is Anderson localization. Once this order gets noisy, then there's a diffusive spreading again. If the noise overwhelms everything right here, then again, this gets suppressed by a quantum Zeno effect. There's lots of effects that you can study with this and simulate in quantum simulation. And also you can study Levy flights and see the hydrodynamic behavior of such a system, the long-term behavior like this. And just to show you my last example, this is a variational quantum simulation that we did. The way I just showed you, we break down the Hamiltonian in pieces and let the system run in an iteration to see how the system iterates until it finds the real values that we do here. And this is now again done for the Schwinger Hamiltonian, finding the ground state. So while the totalization is good for dynamics, this procedure is good for eigenstates. And you see here, this is a Bayesian estimate. And there's many, many points right here which are away from the state here. This is done by deliberation because we really want to make sure we have added a stochastic component to make sure that we are not stuck in, local minima of the optimization regime. The good point right here is, aside from programming for the expectation value, you also can program the computer, say, for variance. And you know, when the variance goes to 0, then you know you have found an eigenstate and you can stop the machine. So it's a sort of self-verifying what you are going to find in such a system. Such calculations have been used for quantum chemistry, calculations in our group, but also in the group of Chris Monroe for water, simple molecules. This is all demonstrations. This is not something that is serious enough to be competitive with supercomputers, but it shows you the way we can do these things and how these calculations are done and what kind of a programming you need in order to get there. Let me finally come to the quantum metrology part. This is a long-standing idea that I had in mind, and this was now worked out then by Peter Zoller and his team, and Raphael Kaubrücker, the PhD student, and the two guys in our lab, Christian Marciniak and Thomas Feldka. What is this about? Suppose you want to do a typical quantum measurement, say the precision measurement of a two-level system for a frequency standard. That's interrogated with the Ramsey sequence. You just have a pi/2 pulse, weigh the system with time, and another pi/2 pulse, and then you find the system either up and down according to the phase evolution right here. And this is a measurement that we did already in 2009 of the qubit transition that we have here. And if you just go in the center, then you find this with very arbitrary, almost arbitrary precision right here. Now the latest measurement was done because this is used as a secondary frequency standard a few years ago by a PhD student of mine, and we can cut down this to about 10 to minus 16. That is the limit that we have for the cesium clock given by PTP. Precision would be better to 10 to minus 17 and beyond, but this is only done in this case here to 10 to minus a few times 10 to minus 16. Okay, what can we do in a quantum way? This is the old-fashioned Ramsey zone as we have it. Now you can actually say, I want to enhance my signal-to-noise ratio. That is what you usually do by adding more and more atoms. But if the atoms are not correlated, then this is just an average that enhances signal-to-noise ratio by the square root of the number or the square root of the time that you spent in order to measure. Here we can do better. If you just have qubits in this case, and let's just take a sequence right here, then we replace these pi/2 pulses right here by unitaries, which are now dependent on certain parameters. So we just give a certain degree of freedom. And these parameters, of course, are done by, evaluated by a computer. They just measure the total excitation of the system, and then the system finds out what kind of unitaries are best used for these two procedures. And in order to do now the optimized version, we just let it go around in a hybrid fashion in the same way, variational answers as I said before. And we iterate, and what we do then, of course, we iterate according to a cost function. That cost function is usually the mean squared error that we get, and of course we have a initial distribution here with the imprecision and the variance, and then we optimize for the real parameters. So when you just have now the interferometer like this, and this is now the interferometer part where this second pi or 2 pulse is 90 degrees out of phase, so you have a sine instead of a cosine, that is where you want to stabilize your interferometer. Then your prior would be that distribution, and this is the noise that you get, shot noise or projection noise. So this is the classical Ramsey. The 00 stands for classical excitation pi over 2, the classical spin coherence that we get, the classical coherent spin state. Now when we do a spin squeeze state, we take use of the Melmer-Sørensen interaction, which is in the language a one-axis twisting operation, so we get the spin squeezed state, and we expect that the noise gets down. That's exactly what we see right here. But otherwise, the behavior of the interferometer is quite similar. But we can do better by just tailoring now the measurement unitary right here, and with this we just enhance the dynamic range. Of course, this is a nicely linear slope, which is good for everything else, and the slope is not as big. It's also good because we can catch it better, but the dynamic range has been enhanced. But the difficulty right here is the noise is slightly bigger. And now we also tailor the input unitary right here, and you see we are always close to the limit that's set here by the quantum limit, at the Heisenberg limit. And to cut the long story short, this is, in summary, what we get. This is the Heisenberg limit that we would get for such a system, and the red points right here show you what we actually getting in the experiment, and of course we get the expected enhancement by the number of n and not just by a square root of n, as seen here by the number of ions. So this is a kind of way you can enhance quantum measurements by using quantum techniques once you have access to the individual qubits, to the individual sites, and once you can control the entanglement. With this, let me just conclude with a few remarks on scalability, how to scale this up. Now, scaling the Eintracht quantum computer requires certain goals and strategies. Of course, you want to have more qubits in 1D and 2D, so that requires better traps. We need better operations, better control, and eventually we will need quantum error correction. The computational power, and we heard this already this morning, requires quantum software, and we need to identify a key problem. The Shor algorithm by itself is not a key problem, not anymore interesting, because other methods have been superseding the need. But the point that I really want to make also for an implementer and for experimentalists is we want to have better predictability. Predictability means once I know the gate error, for example, and I run an algorithm, I want to know how reliable is the outcome, just measuring this from the component status. Usually this is not the case when you just go to IBM, for example, because of all the non-Markovian noise that we have. And this requires that you have a specific error model, and this is currently being investigated in many labs. Scaling down needs less space. You have seen we have already now everything into 19-inch racks, and also miniaturized control hardware. We need to protect things in a passive and an active way, error correction. We need faster gate operations. But then something that's usually also not so much considered is what I mean by scaling out. We need interconnectivity. If we have a modular design, we need also optical interfaces to interconnect these modules to make things bigger and bigger, to control them as much as we can. And finally, we need distributivity. Quantum parallel software is also required. I'm close to the end, so let me see whether this works with this control right here. Let me see how this works. I don't know. Can you just push on the triangle on the red lower hand side, please? Thank you very much. So what is the dream? The dream that we have, of course, that we have finally local logical qubits. A logical qubit is comprised of many qubits, creating the redundancy that's necessary, for example, for error correction. And of course, then we protect this information by error correction, and we want to interconnect them, say, on a chip like this in a lateral and a transversal way. I don't have the time to show you that, but we have succeeded in doing so recently, and we have already larger traps in a collaboration that are manufactured by Infineon, and we really want to get to a network very soon. But I also want to share with you what's a bit in the news these days. There's a lot of fiction about quantum computers. When you see these magazines like Time in 2014 and the last one in 2023, a quantum computer made the headlines. And they made the headlines and many others. You see, for example, statements, quantum computers will replace classical computers. I put a big question mark here, are better than classical computers, question mark. Quantum computers are always faster, sorry, there's a faster missing here than classical computers. That's all not true. I have big question marks here. So let's just put this in the trash bin. What are the facts? The facts are quantum computers are universal computers, but you would not use them to add, say, numbers. Say 1 and 1 is a bad problem for a quantum computer. You would use them for problems that you cannot easily solve on a classical computer. They were completely different from a classical computer because they're using superpositions entanglement. Quantum information, as I could show you, is more volatile than classical information, so it needs to be protected, which is the big issue right now in many labs. And the error correction, on the other hand, works in the quantum world, which is the good news. We just have to do it. This just is not just easy, it is very, very hard work, but we are on a good progress here, and I could go on and give you another lecture on that, because there's plenty that we've learned over the last years. Quantum computers are faster than classical computers, but only for certain algorithms. So when you just look at this, quantum computers are already a reality, small ones, admittedly, but there are ions and atoms and traps, superconducting circuits, photons, and the like. And all of these have green marks. But fact is also, when you just make a reality check, we have currently on the order of about 100 qubits, and at best maybe a few hundred qubits. We have at best 1,000 gate operations, maybe a few thousand these days for certain architectures. But a competitive application, competitive with superconductors, supercomputing stuff, supercomputing centers, requires more like 10 to the 5 to 10 to the 6 qubits and 10 to the 6 to 10 to the 9 gate operations. There's a very wide gap between what exists currently in the lab, or even with small companies, and what is actually necessary to do competitive calculations. And we have to overcome this gap, not necessarily just by technology. This is not only technology. There's a lot of physics to be done before we actually get there. Physics and technology, they need each other in a bootstrapping process in order to get there, and so this is still a lot of work down the road. Currently, we are working with NISQ computers, noisy intermediate scale quantum computers. And this is, I summarize, with more qubits, I mean we are going towards 100 right now. We can have a roadmap going to 1,000. We need better fidelities. We develop 2D traps. But by all means, the holy grail in this area is the achievement of quantum error correction reliably for or what I would say is keeping a qubit alive for the sake of the computation. And then all the rest is relatively easy. Of course, this is done by a large team in my group. Of course, the entire team is taken over by younger people these days. But it's a lot of fun to work with them, and it would not be possible without the help of very many theorists that we have here. And just to show you where we are, this is the airport in Innsbruck, this is where the quantum computer is home, and we have now a company that actually sells these. This is our commercial product. We have sold 3 systems already, works beautifully fine, up to 50 qubits, and if you want to buy one, you would have to contact Thomas Mons, and if you want to see the heart of it, that is the engine. Thank you so much.
Donc merci professeur Blatt. pour cette présentation où vous nous avez permis de mieux comprendre l'état actuel des ordinateurs quantiques à ions piégés et la complexité des systèmes quantiques pour la métrologie. Votre intervention aujourd'hui a mis la lumière sur les perspectives passionnantes pour l'avenir des technologies quantiques. Maintenant, nous poursuivons avec notre deuxième keynote speaker, le professeur Eugène Simon Polczyk, professeur de physique au Niels Bohr Institute à l'Université de Copenhague du Danemark. Il est également le directeur du Centre de Sciences Quantiques Biomedical Novo Nordisk, et le leader du Quantum Optics Center Quantop. Ses travaux couvrent des domaines variés de la communication quantique à la mesure des champs quantiques, en passant par la physique de la matière et de la lumière. Professeur Polczyk est membre de l'Académie royale des sciences du Danemark, fellow de la American Physical Society et de l'Optica Society. Parmi ses distinctions, il a reçu le prix Herbert Walther, le prix Gordon Moore, ainsi que le prix de leadership en recherche de Scientific American. Professeur Polczyk, the floor is yours.
Thank you. Can you hear me? Thank you very much for the kind introduction, and I'm really grateful to the organizers and the Academy for inviting me here and arranging the meeting in this beautiful country of yours. So I'll be talking today about, it will be probably the first full-blown talk on quantum sensing, and I would like to introduce the quantum mechanics in the negative mass reference frame, and hopefully you will figure out what it is by the end of the talk. So let's start with the founding fathers, and here's a simple example that hopefully illustrates the problem, and then we will go through the solution. So this is called the Heisenberg microscope, and the story is that we want to observe the motion of a particle. To observe it, we scatter a photon of it. So we scatter a photon, we still scatter a photon, and the photon gives a kick to the particle. But the problem is, of course, that we know that the particle is at the same time a wave, and the more you focus the light wave to better know the position, the more the light wave diverges afterwards, and therefore the momentum that the particle gains is uncertain. So that essentially leads to a simple calculation of the so-called standard quantum limit in the measurement of motion, where you say, okay, I can measure, let me see if I can get this thing. No, I also don't get it. But anyway, so you look at it, and the position of the particle can be written as the initial position plus the momentum times time over the mass. And if you implement the uncertainty principle, then you quickly arrive at the conclusion that you can only measure the motion of the particle within a certain limit, which is called the standard quantum limit. And in today's talk, I will give you an example of how this standard quantum limit can be actually overcome. So we know about the PR entanglement, we know about the Bohr complementarity. So here is a new kid on the block, quantum reference frame. And well, this is just to show the historical building where my laboratory is, not in this building, but in the neighboring one. And this is the time 20 years ago when we actually landed at the Niels Bohr Institute. And in fact, I would say restarted quantum physics and quantum mechanics there, because for a while at the Niels Bohr Institute, everybody thought that Niels Bohr has actually figured out everything, and there is not much to do. But there is. So let me introduce the family of the quantum oscillators that will be the heroes of today's talk. So one thing is we can take a spin, and it doesn't have to be a spin of a single particle, it can be a spin of 10 to the 10 particles. If we put it in the magnetic field, it will start oscillating at Zeeman frequency, at Larmor frequency, so it's a quantum oscillator. And the projections of the spin are non-commuting variables, so you're not allowed to measure them with absolute accuracy. Same story goes with the mechanical motion. Obviously, the position and the momentum are non-commuting variables, so again, you have a roadblock. And finally, light also has a phase quadrature and the amplitude quadrature, and they cannot be measured simultaneously. Of course, I should refer to the brilliant work of people who've been doing amazing cavity quantum electrodynamics for years, and there are institutions that have pioneered this research and achieved amazing results. And we didn't want to compete with those wise people, so we came up with the approach which, instead of taking some single atoms or a few atoms and coupling them to the cavity mode light, let's just take a large atomic ensemble and see how it can interact with the propagating light field. And use this, you can say, bosonic enhancement in the interaction of light with the large atomic ensemble and encode interesting quantum states in the large collective states of an atomic ensemble. And it is possible to achieve it, in particular, if you are not using an optical transition, but you rather use some microwave or radio frequency transition in the atom, because then the effective wavelength is long, and the entire ensemble doesn't have to be put in the cubic wavelength volume. So this is one of the examples of the device that we're using. It's actually an ensemble of atoms at room temperature, but it is a very special ensemble. It's held in a special glass vessel with certain properties. But the important thing is that, the atoms can run around like crazy at 200 meters per second, and still they don't decohere. Their ground state coherence can be maintained for up to a second. And the principles that you want to follow here is that, first of all, you need long coherence times, and this can be achieved, for instance, by special coatings of the cell walls so that atoms bounce off and they don't lose this coherence. And then the interaction with light should be arranged so that you don't have the which atom interaction. So light interacts with the entire atomic ensemble as a whole. And then you have this bosonic enhancement, and the lifetime can be long, so you can use this device as a quantum memory, as an entangling mechanism, and so on. Do I? Okay. So I'll try to speak lower. Now, let's come up with the quantum model of such an ensemble. So this is a Bloch sphere, and here I have 5 atoms, but in fact we have 10 to the 10 of them. And so let's say that they're all oriented in one direction. And then, of course, there will be the quantum uncertainty of the collective spin, which will be of the order of square root of the number of spins. And within Hallstein-Primakov approximation, you can look around the northern pole of this sphere, and you can approximate it as a plane. And in this plane, you can generate all kinds of collective states. So, for example, if I take, and before we go to the states, you can see that if you take the commutator for the collective spins, then you can actually renormalize it to look like the commutator for x and p, which will be the renormalized projections of the quantum spin as is written in the bottom. So the creation annihilation operator in this case concerns creating or annihilating the collective state of the spin. So let's say if you can flip one of those spins, but not just, number 1 and number 2, you flip them in such a way that you don't know which of them was flipped. So it's a collective excitation distributed over the whole thing. And then you actually generate the first Fock state of this ensemble. And because the Fock state has a higher diameter, so to say, than the ground state, then because of the curvature of the sphere, the energy will go down. It's also clear that the energy go down because you are flipping one of the spin from 1/2 to -1/2. So you put the excitation in this system and you reduce its energy. So this is like the negative mass system. You put in the excitation, you reduce the energy. And this state was reported in this paper. Now if you put this system in the magnetic field, then the spin state begins to precess, and now you have a magnetic oscillator. And this magnetic oscillator includes certain excitations, and in this example it's just a single excitation, but if we're talking about entangled states, there could be multiple excitations as well. And as I said, this can be considered a negative mass oscillator. So how do we measure it? Well, we send light through it. If light is linearly polarized and it goes through the atomic spin which is precessing, then the polarization of light will be oscillating. And this oscillating polarization of light will be measuring the state of the spin. So you put it on the detector, and this, in the upper right corner you see the equation describing the motion of the spin in the lab frame. There is a cosine and sine component of this motion, and they actually present the non-commuting operators. So you try to measure one, you put the back action into the other one. And the first goal to have this macroscopic system in the quantum-dominated regime is to observe this quantum back action of light on the macroscopic atomic ensemble. And again, this is the illustration how this back action builds up. So at the first instance, you measure the projection along the x-axis, and you put the back action in the p, and then you keep measuring and measuring and measuring, and the more you measure, the more quantum back action you observe. And this is the observation. So in this case, the magnetic oscillator was tuned to approximately 1.5 megahertz, and you see the signal, which is dominated by the quantum back action, and the almost ground state of the system is much smaller. Okay, so let's change the gears a little bit and introduce another important component of this business, and that is the Einstein-Podolsky-Rosen entanglement. You've heard about it in the earlier talks, and in this case, this will be the entanglement, not between the position and the momentum for the time being, but between those macroscopic spins of the two atomic ensembles. And in fact, there is one-to-one correspondence between the macroscopic spins and x and p operators, which is written here, comes from the commutation relation. And there is a necessary and sufficient condition for this entanglement, and I will give you a very simple geometric description of this entanglement in a minute. So we have two of those ensembles. One is oriented originally up, and this is the negative mass oscillator. The other spin down, it's a positive mass oscillator. You send light through, you make a measurement. And in this measurement, you can actually do some math, but the important thing is that in this rosy box, you see that by measuring the Stokes parameter of light propagating through the system, you can observe non-destructively and simultaneously the sum of the z components of those spins and of the y components of those spins. And this quantum non-demolition measurement allows you to know essentially the angle between those two macroscopic spins, despite the fact that they are defined by non-commuting variables for a single system. So we've done this experiment some time ago, and we observed that we can generate a state which will be, for the two systems, the two spins will be more parallel than the minimal uncertainty state for each of them allows. And this apparently can be used for various kinds of sensing, and we have done that since then on many objects, because, you know, if you have two exactly anti-parallel spins, and then you apply your perturbation, for example, the magnetic field from your brain or from your heart to one of them, and measure again, then you can measure this perturbation without the limitations which are posed usually by quantum mechanics on a single spin. So this you can call measurement in the negative mass reference frame, because one of those spins is in a negative mass system effectively, and the other in the positive mass system. So we can measure amazingly weak magnetic fields and use this for various kinds of diagnostics. Okay, and just kind of to flash our recent developments in this domain, we have founded the Copenhagen Center for Biomedical Quantum Sensing, where we use this kind of entanglement for different types of modalities. We can do various measurements with the sensitivity not limited in principle by the quantum states, uncertainties. Okay, so we take a deep breath and we change the gears. And what I want to talk about in the remaining part of this discussion is how do we use this negative mass reference frame represented by the spin polarized atomic ensemble to detect the real mechanical motion. So we called it some time ago trajectories without quantum uncertainties in the negative mass reference frame. And other people, Carl Caves and his colleagues, are using the term quantum mechanics free subspaces. So it's the same story. And the story is you have a classical trajectory. If the particle is here at the point in time, then you know where it will be in the next point of time. And in the quantum domain, the quantum trajectory in principle is unknown, it diverges. And the point is that if we introduce the correct reference frame, then we can in fact make the quantum trajectory look like a classical one. That is to say, we can trace the motion of an object in principle without limitations of the Heisenberg uncertainty if we make a measurement with respect to a certain reference frame. So a brief history of this business is not so brief, but I will go through it real quick. Aronov and colleagues have talked about quantum reference frames quite some time ago. Roy Gleiber introduced the inverted oscillator, and then unrelated to those wonderful works, we have done this work where we demonstrated that two spins can be entangled, and one of them is in the effective negative reference, mass reference frame, the other one is normal, and then you can make the measurement of the motion of the spin, which is below the Stern quantum limit of the uncertainty. And then there was more interesting theoretical work, and more interesting theoretical work, and more interesting theoretical work. And then the next generation of experiments came about from our group and from the groups in other countries, in Switzerland and in the US and in Finland and so on. So, quantum mechanical oscillator, mechanical in the real sense. So there is an oscillator and it oscillates, and you can calculate at zero temperature what would be the so-called zero-point fluctuations. And you can calculate what is the uncertainty corresponding to those zero-point fluctuations. And for our relatively macroscopic oscillators, it's about a femtometer. Well, a femtometer is something that you can easily measure with light. And again, of course, it's an oscillator, and so there is the uncertainty between the position and the momentum. And a good measurement of x imposes the uncertainty on p and the other way around. So you have this quantum back action of measurement. And for an oscillator is like that. But the point again is, as I've shown you already, despite the fact that if you do continuous measurements, you pile up the back action more and more and more, still, if you make a measurement in the suitable reference frame, you are allowed to measure perturbations in both position and momentum with, in principle, arbitrary accuracy. And the 3 steps to that is you have to define the trajectory relative to the quantum reference frame. This reference frame should have the effective negative mass. You have to create an entangled state between the reference frame and the object of interest, and then you measure. So let's look at the really, really simple algebra of this business. And I just, forget about the operators here. Let's talk about it in the algebraic terms. So we are allowed to create an entangled state between the two systems. And this is back to Einstein-Podolsky-Rosen example. And we are allowed to know the difference between the positions and the total momentum. Good. Is that enough? No. Because if you want to measure the position of one of the systems as a function of time with respect to the x0 system, then it will be the difference of the initial positions plus the difference between the two derivatives, I put mass to 1, times time. And what you get in the last line is the difference of the positions and the difference of the momenta. And they don't commute. But if you now introduce a negative mass, then the minus sign is changed to the +1 in the momenta. And then the trajectory is defined by the difference of the positions and the sum of the momenta. And you can measure those with arbitrary accuracy. And therefore, you can have the trajectory of one system with respect to the other with, in principle, unlimited uncertainty. And this is what we essentially have demonstrated. So the first experiment was, let's take the spin ensemble. Rainer, can I borrow your pointer maybe? Fantastic. Our community has always been so friendly and helping each other. So that's the experiment where we took the atomic spin ensemble and entangled it with the little membrane, a mechanical oscillator, by sending light through. So that's the atomic ensemble. That's the mechanical oscillator, the central part here oscillating at about a megahertz frequency in some very sophisticated frame. And you measure on light, and what you get here is the quantum noise of light, plus force terms, plus the quantum back action from atoms here, and the quantum back action from the mechanical object. And again, you can think of your atoms as the renormalized oscillator, and the point being that if you choose the interactions in the correct way and you tune the frequencies in the right way, then the quantum back action is gone, and you can make a measurement which will give you the force terms with, in principle, arbitrary accuracy. So again, in the rotating frame, you can look at it as the difference between the x in the lab frame minus the x naught of the reference oscillator, and then it will be the difference of x components times cosine and the sum of the p components times the sine. And the sum comes from the fact that it's a negative mass reference frame. And then, of course, you can measure this and that by creating entanglement, and then you know your trajectory with, in principle, limited accuracy. So this is our beautiful mechanical oscillator in this experiment, and I would like to credit my colleague Albert Schleiser and my student Yegish Tsaturyan for fabricating those devices, which are amazing. They have the Q factor of 10 to the 9, and that's why by shining light on those, we can actually cool them down to the ground state of motion. So here is the evidence that this system, the mechanical membrane placed between the two mirrors, so the mechanical membrane is oscillating, and you have a standing wave of light here, and when you have a mechanical dielectric object oscillating in the light field of the cavity, you can measure its position, but you can at the same time understand that you are putting the quantum back action because of simply the shot noise of light on this mechanic, on the object. And so we need to somehow fight against the both noise of light and the quantum back action. And so we are again, in this case, having a high cooperativity, meaning that we are dominated by the quantum back action, and the ground state is nearly small. So if we cancel this, then we can get to the measurement at this accuracy. Again, the spin oscillator is what you have already seen, and it has a very good Q factor and very good properties, and as I mentioned to you already, it can be initiated so that it corresponds to the 0 Kelvin temperature in its spin motion. So that was the paper where we demonstrated this entanglement between the motion of the membrane and the motion of the spin oscillator in the negative mass reference frame. And the negative mass, again, is illustrated by the fact that the initial state of the oscillator is here, and if you generate an excitation, then it has lower frequency than in the mechanics, where when you generate excitation, the energy is higher. Right, so without going into too much in this business, note that this is a logarithmic scale, so this is the measurement on the mechanical motion, which is dominated by the quantum back action. And this is the measurement on the atomic system, again dominated by the back action. And in this case, the magnetic oscillator is simply tuned away from the mechanics. And now we tune the magnetic oscillator back onto the same frequency as the mechanical oscillator, and instead of increased quantum back action, we get it substantially reduced. Again, it's a log scale, so the reduction is like 6 dB, which is a factor of 4. So we put together two noisy systems, and we get much less noise in the end, so that's good news. It's an illustration of exactly this fact. Those are the heroes in the lab. And in the next experiment, we actually took one step further, and we demonstrated that indeed those two systems are entangled. And let me skip this one. But here I need some help. Can we please initiate this motion? So, no, forward please. No, we need to go forward, thank you. One step forward. Forward. Still forward. It's a very nice animation. Well, doesn't want to work. Anyway, thank you. Let's forget about the animation. So essentially the story is that if you would have seen this animation, then you would see in real time the trajectories of motion of the two oscillators, and you will see that they are near each other with the accuracy which is better than the quantum limit of sensitivity. So this is where you were supposed to see this animation. So this is the uncertainty corresponding to the ground state of one oscillator. And this, yes, thank you. So now you see that the two oscillators actually going in the phase space, and they are following each other, roughly speaking, to within this blue circle. And the size of the blue circle is smaller than the size of the ground state uncertainty. This means that we essentially can measure the two oscillators in such a way that we force them to walk in tune. Thank you very much. Excellent. Thank you. All right. So the last hour or so, I will tell you about the application of this method to the detection of the gravitational waves. And the gravitational wave detection is done by the huge interferometer, where one mirror is suspended and the other mirror is suspended, and the gravitational wave, which is a quadrupole wave, misbalances this interferometer, and people shine light on it and make a measurement of the interference, and the motion of those two mirrors tells them that the space has been distorted in the quadrupole fashion, that is to say, a gravitational wave came by. It's an incredibly precise measurement. They're measuring to within 10 to minus 20 of the distance, but they want to do better. And they have their ways to do better, but we propose our own way to improve the sensitivity, and we want to combine this interferometer with our negative mass oscillator. And in simplistic terms, if the interferometer of LIGA has this kind of response, which is the normal response of the driven oscillator, and the oscillator is those mirrors, then if I combine it with the atomic response, which is matched to that one but has an opposite sign, then I will cancel all the noise in the system. Again, if I combine the normal trajectory with the negative mass, then I can measure better than the standard quantum limit. And in fact, this device is already operating at the standard quantum limit. So this is the response of the system as a function of frequency between a few kilohertz and a few hertz, and they are almost touching the standard quantum limit. And in fact, in the very recent experiments, they can overcome the standard quantum limit in a certain band by using 300-meter long cavities. And what we want to claim is that we are ready to substitute the 300-meter long cavities with a 10-centimeter long cesium cell. Hi. Well, this is the team, and normally they are oriented in a different direction, but that must be the effect of the spin orientation. Anyways, so we need several steps between the measurement that I told you about with the microscopic membrane and atomic spin. We need to change a few things here. First of all, the atoms like their own wavelength, but the LIGO people like their own wavelength, and none of those two systems is negotiable. So instead of just using one laser beam going through both systems, we need to use two entangled light beams, one to probe atoms and the other to probe the sensor, which is the gravitational wave interferometer. And so we're following the proposal that we have put forward together with my dear colleague Farid Khalili and also with Emil Zeuthen. Essentially, we need two entangled beams and we need the atomic oscillator in the negative mass reference frame in a suitable frequency range. So, real quick, the basic steps. So we have two entangled beams. One of them is talking to the sensor, for example, to the LIGO interferometer. The other one is talking to the negative mass oscillator. We make a measurement here and we make a measurement here. So what we measure with this detector is the shot noise of light, spin noise, and the back action of this light on the spin oscillator. What we measure here, for example, in reflection from the gravitational wave detector, is again shot noise of light, the force, that is a gravitational wave detection, and the back action. And notice that here we have the p quadratures of light, and here we have the x quadratures of light. But the entangled light has correlations between both those and those. However, it's not enough, because if we only had the normal kind of mass configuration, then there will be again the difference between the p's and the difference between the x's. They don't commute. So we have to use the negative mass oscillator, which will make the susceptibilities here and here of opposite signs, and then we will have this one cancelled and this one cancelled, and will appear only with the force terms. So 6 years ago we embarked on this experiment, and now I'm happy to report the first results. Oh God, sorry. So this is just to show you that the light source that we're producing is really remarkable. It is a two-color entangled light source, which is about 9 decibel below the shot noise limit, down to the frequencies of a few hundred hertz, and it's entangled down to 100 hertz frequency. So that's one necessary condition. The other necessary condition is that we need to have the spin oscillator dominated by the quantum noise. And so we do have it, and we have it down to the frequencies which are really low, kind of down to a kilohertz range. According to the simulations, we're supposed to be able to suppress the quantum noise in the broad range of frequencies, but the experiment is not yet working in the few hertz or 100 hertz range. The experiment is working in the range of a few kilohertz, but the bandwidth is wide enough that is it compared to the central frequency. Well, I'm sorry, this is just useless. So let me show, and this is even better. So you don't see my experimental graphs. Sorry about that. There were experimental graphs there, and those experimental graphs were showing the noise reduction below the quantum limit of about 3 decibel. Well, now it's 2 here, but we have it better a little bit. And it's in the region between 10 kilohertz and 20 kilohertz. There are other applications of this system which can be used for quantum measurements and quantum communication between different sites. And this is my conclusion. So I introduced you to the macroscopic objects which can be entangled and used for precision measurements and remote sensing, and quantum superposition states of distant macroscopic objects is a promising platform for testing the boundaries of quantum mechanics. Thank you for your attention.
Polzik, pour cette exploration des limites de la mesure en mécanique quantique et pour nous avoir introduit à l'idée fascinante du référentiel de masse négative et ses différentes applications. Nous sommes vraiment impatients de voir les autres applications, surtout, comme vous l'avez dit, pour la gravitation quantique et autres. Alors enfin, pour clôturer cette séance par une présentation, donc j'invite professeur Mostafa Mansour de l'université Hassan II de Casablanca, dont les recherches portent sur les corrélations et l'intrication quantique, les batteries quantiques, l'interaction entre l'information quantique et la relativité dans des systèmes complexes. Aujourd'hui, professeur Mansour va nous présenter ses derniers travaux sur les applications technologiques de l'information quantique, en particulier dans le domaine des batteries quantiques. À vous la parole, professeur.
Perpétuel de l'Académie de m'avoir invité à intervenir dans cette grande manifestation organisée par l'Académie Hassan II des sciences et techniques. Je remercie également les organisateurs. C'est bon? Je remercie également les organisateurs de m'avoir invité aussi et de leur accueil aussi. Ma présentation explore les opportunités offertes par l'information quantique et les avantages aussi, avec un focus particulier sur le concept batterie quantique. Bien sûr, tout le monde connaît l'information quantique. On sait que l'information quantique, c'est une nouvelle science qui se base sur les lois de la mécanique quantique afin de traiter, transférer, transmettre l'information d'une manière totalement différente de ce qui est classique. L'information quantique, il a plusieurs défis et opportunités aussi. Parmi ces défis, on trouve le calcul quantique avec un ordinateur quantique qui est capable, en utilisant les lois de la mécanique quantique telles que la superposition, le parallélisme quantique, d'exécuter des tâches qui sont impossibles avec un calculateur classique, bien sûr, en redéfinissant les frontières de la complexité algorithmique et aussi en pouvant faire des calculs qui sont impossibles avec des calculateurs classiques. L'étape la plus fondamentale, c'est le sycamore de Gogol, qui a marqué une étape décisive dans ce domaine de calcul quantique, en revendiquant ce qu'on appelle la suprématie quantique. Le deuxième défi de l'information quantique, c'est la communication et la cryptographie quantique. Là, c'est la Chine qui domine. Donc, la cryptographie quantique, on essaye, bien sûr, en utilisant les lois de la mécanique quantique, telles que le principe d'incertitude de Heisenberg, le théorème de non-clonage, de transmettre de l'information d'une manière très sécurisée. Le plus important dans la communication quantique, c'est que la sécurité de la communication, il n'est pas assurée par la complexité du code de cryptage, mais uniquement par les lois de la mécanique quantique. Ici, je pense que l'étape la plus importante, c'est ce projet chinois. Mais les experts chinois, ils ont tout fait ici. Donc, ils ont distribué les clés à longue distance. Il y a de la communication intercontinentale, en ouvrant la voie aussi à des réseaux quantiques ultra sécurisés. Le troisième défi de l'information quantique, c'est la métrologie quantique. Notre professeur Serge Haroche a déjà parlé de ça. Donc là aussi, la métrologie, c'est un peu le carrefour entre la mécanique quantique et la théorie de mesure, en essayant de mettre en place des gadgets qui se basent sur la loi de mécanique quantique avec une précision inégalée. L'exploit, parmi les exploits, c'est cette horloge aussi qui est Astrontion, dont les concepteurs annoncent qu'il a atteint une précision inégalée d'une erreur d'une seconde sur 33 milliards d'années. Et le dernier défi de l'information quantique, et qui fera l'objet de mon exposé, c'est le concept de batterie quantique. Dans ce domaine de batterie quantique, on essaie aussi d'utiliser des lois de la mécanique quantique, telles que la superposition, l'intrication, la cohérence quantique, afin de mettre en place des batteries qui sont capables de stocker, transférer, transmettre l'énergie d'une manière plus efficace et plus cohérente, et aussi avec un temps de chargement très rapide et qui dépasse de loin tout ce qui est classique. Et bien sûr, le travail fondateur de ce domaine de batterie quantique, c'est ces deux physiciens, c'est Robert Aliquet et John Fass, qui ont fait un travail pionnier et fondateur, dans lequel il explique que ce batterie quantique, il peut se baser sur un concept de base qui est le qubit. C'est la cellule de la batterie, c'est un qubit, c'est un système quantique à deux niveaux et qui peut être chargé via une pulsation. Donc c'est le travail de base. Et donc un batterie quantique, on peut le modéliser par un qubit avec un deux états. L'état déchargé, c'est l'état fondamental, c'est la batterie non chargée. L'état excité, c'est la batterie chargée. Et il suffit d'avoir une pulsation résonante pour faire passer le qubit de l'état fondamental à l'état excité. Vous avez votre batterie qui est chargée. Donc c'est un modèle simple d'une batterie quantique ou bien d'une cellule d'une batterie quantique. Un autre modèle plus robuste, c'est le fait d'un 3 qubits. Là, vous avez deux modes de chargement. Vous pouvez passer par, là, bien sûr, l'état 0, c'est l'état fondamental, et l'état 2, c'est l'état où la batterie est totalement chargée. Et là, vous avez deux processus de charge. Vous pouvez passer directement de l'état 0 à l'état 1 et après à l'état 2, ou bien expérimentalement, on peut régler votre pulsation électromagnétique pour faire passer directement l'atome ou la molécule ou n'importe quoi, de l'état 0 directement à l'état 2, et vous pouvez gagner en termes d'efficacité aussi et en termes de temps de chargement. Bien sûr, le processus de chargement, c'est simple, c'est l'interaction de votre batterie avec un chargeur. Le chargeur, il peut être classique ou quantique. Et là, vous avez un hamiltonien qui régit un peu le tout. C'est l'hamiltonien de la batterie plus l'hamiltonien du chargeur plus l'hamiltonien d'interaction. Et un chargeur typique, c'est un autre qubit qui peut servir de chargeur pour charger un qubit. Et bien sûr, il existe aussi des modèles de chargeurs classiques qui utilisent soit des pulsations électromagnétiques ou une autre interaction. Le mieux, c'est de faire passer le qubit d'un état à un autre. Bien sûr, ce sont les deux modes de chargeur, soit chargeur classique et chargeur quantique. Là, ce sont les concepts de base sur lesquels se basent, ou bien ce qu'on appelle les indicateurs de performance des batteries quantiques. Il y a ce qu'on appelle l'ergotropie, c'est-à-dire le travail qu'on peut extraire à partir d'une batterie quantique. Il y a aussi la capacité, c'est la quantité de charge ou d'énergie qu'on peut stocker dans une batterie quantique. Il y a la puissance de charge, c'est-à-dire la vitesse avec laquelle on peut charger ou décharger une batterie. Et aussi le travail, c'est exactement l'ergotropie, mais il faut diminuer l'erreur expérimentale, c'est-à-dire la perte d'énergie qui peut se faire expérimentalement. Là, le processus de chargement, d'une manière générale, si on remplace le cas simple d'un qubit ou un qubit, un système à 3 niveaux, on peut remplacer l'état de système par une matrice densité, le cas général. Donc, il faut passer d'un état énergétiquement bas vers un état énergétiquement haut. Là, c'est le processus de chargement. L'inverse, si vous passez d'un état qui est chargé à un état déchargé, là, c'est l'inverse, c'est le processus de déchargement. Un autre article aussi de base dans ce domaine de la batterie quantique, c'est ce monsieur le premier qui a mis un protocole pour charger un qubit d'une manière optimale. Et aussi, ils ont proposé que le fait qu'on utilise des qubits intriqués, on peut accélérer le processus de chargement. La première expérience qui a été faite pour mettre en place une batterie quantique, ce monsieur, c'est James Quaish, en se basant sur les cavités organiques et la superabsorption. La cavité organique, il peut accélérer la superabsorption, donc ce qui va emmener à une accélération de la charge de la batterie quantique. C'est ce monsieur qui a inventé ce mot que le futur de stockage d'énergie sont les batteries quantiques. Ce monsieur James Quaish, il a signé avec nous un papier dernièrement. Ce papier, il est sur l'archive. Donc on a travaillé sur un modèle bipolaire, deux bipoles, qui interagissent via une interaction bipolaire, plus une interaction DM symétrique, plus une interaction antisymétrique. Je vais expliquer à la fin de cet article si on a un peu de temps. On a continué dans un autre article qui se base, un modèle de batterie quantique qui se base sur un modèle de Kitaev. S'il y a un peu d'eau. Donc là, c'est un autre article aussi qui est sur l'archive, sur lequel on s'est basé sur le modèle de Kitaev aussi. C'est un deux spins qui interagissent et on a essayé de bâtir un modèle sur cette base. Un troisième article qu'on a soumis aussi, c'est le fait qu'on a une batterie quantique qui se base sur deux qubits supraconducteurs qui interagissent par une interaction de couplage, un couplage, et aussi via les capacités de Josephson. Mais avant d'expliquer un peu le contenu de ces articles, il faut expliquer un peu le modèle d'Alick, le modèle de base qui a été explicité par Robert Alick et John Fans. Donc pour Robert Alick et John Fans, c'est quoi une batterie quantique? C'est le cas général, il est représenté par un Hamiltonien avec des énergies qui sont, on exige qu'elles soient dégénérées et qui sont classées par ordre décroissant. Et bien sûr, l'énergie moyenne, bien sûr, le système est représenté par une matrice densité, donc l'énergie moyenne, il est bien défini par cette relation. Donc, une fois, bien sûr, l'évolution de votre état est régie par une équation de type von Neumann. S'il y a de la dissipation, on peut exiger qu'il existe un autre terme de type Lindblad, comme ça, il régit la dissipation de votre énergie. Et vous avez une évolution, dans ce cas, on a une évolution unitaire, et vous avez l'évolution de votre état. Donc, et une fois que votre état évolue d'un état initial vers un état final, vous pouvez calculer, soit vous pouvez calculer le travail que vous pouvez extraire à partir de votre état, ou bien vous pouvez calculer le maximum du travail que vous pouvez extraire via des opérations unitaires que vous pouvez appliquer à votre matrice densité, votre état de système. Là aussi, il a introduit la notion d'une matrice densité passive ou un état passif. Un état passif, c'est quoi? C'est l'état où on ne peut rien extraire. C'est l'état limite où on ne peut pas extraire de travail. C'est-à-dire, on fait passer votre système d'un état à un état passif, où l'état passif, il est défini comme l'état où on ne peut rien extraire. Et bien sûr, la différence entre les deux, c'est exactement l'ergotropie ou bien le travail qu'on peut extraire à partir de la quantité d'énergie qu'on peut extraire de votre batterie quantique. Là, si c'est selon ce théorème, c'est quoi un état passif? Bien sûr, il existe une formule. C'est quoi un état passif? Aussi, il y a une construction canonique. À partir de n'importe quel état de système, on peut définir un état canonique correspondant qui est un état passif. La construction est simple. Donc, on peut définir à partir d'un état initial. Après, on peut construire un état passif en réarrangeant un peu les valeurs propres. Et la différence sera le travail qu'on peut extraire à partir de notre batterie quantique. Parmi les exemples types de l'état passif, c'est l'état gypse. L'état gypse, les valeurs propres ou les populations, ils sont ordonnées via ce facteur de Boltzmann. Donc, ils sont déjà ordonnés. Donc, c'est un état type. Et d'ailleurs, ce qu'on utilise comme état passif de tous nos articles, c'est l'état de gypse comme état passif. Là, c'est juste l'explication. Donc, comment faire pour extraire dans cette approche d'Aleki. Donc, d'abord, il choisit l'état gypse comme l'état passif. C'est l'état de base sur lequel on travaille. Après, il va considérer que le max d'énergie qu'on peut extraire, il est régi par cette dernière relation, c'est la trace, c'est l'énergie moyenne de votre état, moins l'énergie moyenne de l'état gypse correspondante. Après, c'est l'ENA, c'est ça. Après, il va exécuter des opérations globales. Si on choisit une copie de notre état, il faut exécuter des opérations globales sur votre état afin d'extraire le maximum d'énergie. Et là, dans cette opération globale, il introduit des permuttateurs qui vont introduire quelque chose qui ressemble à l'intrication entre états. Et que cette intrication, ce comportement collectif des états, il est nécessaire pour faire extraire un max de quantité d'énergie à partir de votre batterie. Donc, c'est l'approche de Aleki. Donc, sans entrer dans les détails, ça, on utilise un théorème de compression quantique. On fait passer d'un système de dimension supérieure à une dimension de sous-espace typique de dimension inférieure. Et aussi, on aura des opérateurs qu'on appelle opérateurs typiques là, qui relient un peu les deux espaces et qui sont ces opérateurs de type global qui vont générer cette relation-là qui nous permet d'extraire le maximum d'énergie à partir de notre batterie. Maintenant, je passe à nos articles. Notre premier article c'est ça. Non. C'est ça. Donc, notre premier article, c'était des batteries quantiques qui se basent sur des moments dipolaires. Et en essayant d'utiliser des ressources quantiques telles que la cohérence, la discorde et la concurrence. Donc, on a considéré un modèle avec trois interactions, une interaction dipolaire, une interaction DF de type symétrique et une interaction KSEA de type antisymétrique et bien sûr des champs magnétiques qui s'appliquent sur les deux spins. Et on a considéré notre Hamiltonien. Bien sûr, l'état de gypse, c'est puisqu'on a considéré que le système il est en contact avec un thermostat en équilibre à température T. On a considéré notre système. Et on a considéré le cas où le système il est ouvert. Il est régi par une équation de type Lindblad. Et, bien sûr, dans ce cas, on a deux choix. Soit qu'on considère, puisqu'il s'agit de deux spins, soit qu'on considère que l'état fondamental il est 0,0 ou l'état de gypse. Et bien sûr, le type de chargement, on a considéré le type de chargement, soit que les qubits sont parallèles, c'est-à-dire qu'ils ne sont pas intriqués, soit qu'ils sont intriqués. Et bien sûr, le chargement, on a considéré le chargeur via cet Hamiltonien, et vous voyez, il y a un opérateur X, l'opérateur delta 1X, c'est l'action note. Note, lorsqu'il agit sur un qubit, il fait passer le qubit de l'état fondamental à l'état excité. Donc, c'est juste l'écriture de notre Hamiltonien qui va agir. Donc, et bien sûr, en prenant l'état thermal comme état de base, en prenant cet Hamiltonien comme état, celui qui va décrire le chargeur, on fait interagir ce chargeur sur notre état et on calcule un peu nos quantités. On calcule l'ergotropie, on calcule la capacité et on calcule le travail qu'on peut extraire à partir de notre état. Mais avant de cela, afin de relier un peu ces performances de notre batterie à tout ce qui est intrication et ressources quantiques, on a calculé quelques mesures. On a calculé la concurrence comme mesure d'intrication, on a calculé la CL1 comme mesure de la cohérence de notre système, et on a aussi calculé la discorde quantique comme mesure des corrélations au-delà de l'intrication. Là, on a tracé on a tracé toutes les figures pour les trois ressources quantiques, à savoir la cohérence, la discorde et l'intrication. Et on a remarqué que la cohérence est la plus robuste. C'est elle qui demeure en bleu. La cohérence en bleu, c'est elle qui demeure, c'est la plus robuste, c'est la ressource la plus résistante si la température augmente. Face au thermal noise, c'est la ressource la plus robuste. On a considéré aussi, donc c'est juste, donc c'est la plus robuste. On a remarqué aussi, désolé, c'est ça. On a remarqué aussi que les paramètres du système, c'est-à-dire les paramètres, l'anisotropie, l'intensité de l'interaction DM, l'intensité de l'interaction KSOA, il influence le comportement des ressources quantiques. Et du moment qu'il impacte les ressources quantiques, il impacte les performances de la batterie quantique. C'est-à-dire en ajustant les paramètres dans le système, on peut influencer les performances de notre batterie quantique. Il suffit d'ajuster notre système avec des paramètres à des valeurs précises, on aura une batterie quantique avec une performance bien définie. Donc c'est ça, donc on a montré que tous les paramètres impactent un peu l'évolution des corrélations quantiques et des ressources quantiques qu'on a sur notre système. On a aussi étudié le fait que si le système il est régi par, ou là il est soumis à un déphasage, qu'est-ce qui se passe? On a montré aussi que toujours la cohérence est la plus robuste. C'est elle qui résiste soit au thermal noise, soit au fait de déphasage. Et par la suite, on va garder que la cohérence qu'on mesure, consistance des ressources quantiques qui existent dans notre système, et on va essayer de corréler un peu les performances entre batteries quantiques avec la cohérence. Donc là aussi, on a constaté que la cohérence est toujours la plus robuste, et aussi que les paramètres de notre système, ils impactent l'évolution des ressources, même dans le cas où le système il est ouvert. Et après, on a passé au comportement des indicateurs de performance dans notre batterie quantique. Comment il évolue? Et là, on a constaté que, exemple dans le premier, on a constaté que ce paramètre d'anisotropie axiale, delta, il agit fortement sur la performance de la batterie. C'est-à-dire avec un delta très élevé. Donc si on arrive à canaliser ou à maîtriser les paramètres dans le système, on peut avoir un temps de chargement simple avec un maximum de quantité d'énergie qu'on peut extraire de notre batterie. La capacité, il ne change pas via le temps, il change uniquement en fonction des paramètres qui régissent notre système. La cohérence aussi, il évolue. Donc, on a fait toute une étude en fonction des paramètres qui régissent notre système, et on a montré que, en ajustant les paramètres du système, on peut influencer les ressources quantiques existantes entre les deux qubits, et par la suite, on peut améliorer la performance de notre batterie quantique. Bien sûr, c'est une étude purement théorique, on n'a pas fait d'expérience, c'est juste une analyse en se basant sur la simulation. Et bien sûr, on a montré qu'il existe des paramètres qui ont plus d'influence que d'autres. Il y a des paramètres que leur influence est négligeable, mais des paramètres tels que delta, il influence beaucoup le comportement de la batterie quantique. S'il est bien maîtrisé, on peut ajuster les performances de la batterie quantique. Là aussi, on a montré, en fonction du champ B, là aussi, là ce qui est important, on a remarqué un comportement un peu contradictoire. Alors que B, il agit négativement sur les ressources quantiques, il agit positivement sur les performances de la batterie quantique. Si on augmente B, il impacte négativement les corrélations quantiques qui existent entre les deux qubits, mais si on augmente B, il améliore un peu les performances de la batterie quantique. Donc avec un champ magnétique B un peu élevé, on peut améliorer un peu les performances de notre batterie quantique. On a remarqué aussi que la puissance, donc il y a deux étapes, en phase de chargement et en phase de déchargement. La capacité reste toujours constante. La capacité, c'est la différence entre l'état excité et l'état fondamental. Donc il est indépendant du temps. Il dépend uniquement des paramètres du système et de la température aussi du système. On a aussi étudié le comportement de ces performances en fonction de la température, et on a aussi remarqué que la température impacte négativement les performances de la batterie. Donc, chaque fois que la température augmente, les performances diminuent dans la batterie. à savoir l'ergotropie, la puissance et la capacité. Donc, chaque fois que la température augmente, il impacte à la fois les ressources quantiques qui existent, c'est-à-dire l'intrication qui existe entre les deux qubits, il impacte négativement les performances de notre batterie quantique. Et aussi, on a étudié également l'intensité de cette dernière interaction qui est symétrique, le KSA, et on a montré aussi qu'elle aussi, il influence un peu les performances de notre batterie quantique, à part la capacité qui reste constante, il change uniquement avec la valeur affectée à cette interaction. Et de même pour l'interaction de M. Donc la conclusion, c'était quoi? C'était qu'il fallait ajuster les paramètres dans le système. De cela, on peut ajuster les ressources quantiques et à partir de là, on peut ajuster les performances de notre batterie quantique. Donc, si on veut bâtir une batterie quantique en se basant sur ce modèle, il fallait choisir les bons paramètres, il faut les ajuster. Comme ça, on aura une batterie quantique avec des meilleures performances. Dans un deuxième article, on a étudié je ne sais pas, est-ce que c'est bon pour le temps? C'est bon? Donc, pour le dernier article, c'était la performance en se basant sur un qubit supraconducteur. Là aussi, on a considéré un nouveau modèle, c'est 2 qubits supraconducteurs, et on a essayé d'étudier les performances de la batterie quantique en se basant sur le couplage entre les 2 qubits supraconducteurs et sur la capacité de Josephson. Un couplage de Josephson qui est léger. Là aussi, on a fait le même modèle. On a considéré un hamiltonien de notre système. L'état thermique, c'est toujours l'état de base, c'est l'état thermal, puisque c'est l'état passif. Et on a fait évoluer, on a appliqué un hamiltonien qui va charger notre batterie. Et on a étudié le comportement à la fois des ressources quantiques et des performances de la batterie quantique. Et on a montré aussi dans cet article qu'il fallait ajuster un peu les paramètres. Parce que nous, dans cet article, on a proposé une solution plus expérimentale. C'est-à-dire, si on arrive à faire ça, ce qu'on va gagner en termes de performance de la batterie quantique. Donc, et on a montré aussi que ce comportement, il varie en fonction des paramètres qui régissent le système. Il varie en fonction aussi, et même les ressources aussi, ils seront impactés par, et dans ce cas aussi, il fallait ajuster les paramètres dans le système. Il fallait ajuster les paramètres pour avoir une batterie quantique qui se base sur le modèle avec des meilleures performances. Donc, et je passe directement à mon dernier slide. Donc, c'est juste, on a refait tous les calculs possibles pour calculer un peu les performances de notre batterie. À la fin, donc, je ne sais pas, donc, juste un rêve, si on arrive un jour à bâtir une batterie quantique marocaine, donc, et sur ce rêve, je clôture ma présentation.
Donc, merci, professeur Mansoul, d'avoir partagé avec nous vos travaux sur... je vous en prie, vous pouvez prendre place. D'avoir partagé avec nous vos travaux sur la modélisation et la simulation des différents modèles afin de pouvoir optimiser les performances des batteries quantiques. Maintenant, on passe à la séance de discussion. Donc, c'est une séance de 30 minutes qui va rassembler des chercheurs de différentes universités marocaines. Il s'agit de 4 chercheurs d'ailleurs. Et qui sera animé, ou plutôt modéré, par professeur Raja Sharqawi et rapporté par professeur El-Mukhtar Sassi, tous deux membres du Collège des sciences physiques et chimiques, et bien sûr membre résident de l'Académie Hassan II des sciences et techniques. Je vous cède la parole, chers collègues.
Merci, Madame la directrice des séances. Donc, nous avons eu le plaisir d'écouter pendant cette session 3 présentations qui ciblent les avancées récentes et les applications des technologies quantiques dans différents domaines. Alors, nous avons la première présentation, s'est concentrée vraiment sur les principes fondamentaux et les applications des ordinateurs quantiques en mettant l'accent et les défis liés à la fiabilité, à l'extensibilité des systèmes à ions piégés. La deuxième explore les nouvelles approches pour améliorer la précision des mesures en mécanique quantique, notamment, et ça c'est très important, via un cadre de référence à une masse négative avec des applications dans la métrologie et la détection des ondes gravitationnelles. Et enfin, la dernière, et dont on est fier parce qu'elle est marocaine, la troisième met en évidence le rôle des batteries quantiques dans l'optimisation du stockage. Tout le monde sait que c'est un problème quand même important dans le monde, et de l'extraction d'énergie en analysant le potentiel. Alors, ceci, bien sûr, reste théorique, mais il peut être très utile dans plusieurs domaines, comme la cryptographie, la métrologie et bien sûr le stockage d'énergie. Alors, je vais tout de suite passer à mes collègues. Alors, je prends dans l'ordre du programme. Donc, j'invite le professeur Mohamed Salah de l'université Chouaib de Kali à El Jadida. Vous pouvez poser vos questions ou votre commentaire, bien sûr, dans la langue qui vous plaît, bien sûr. Allez-y, professeur.
Merci, Madame Raja Sharqawi. Firstly, I like to congratulate Professor Blattreiner, Professor Eugene Simon Polzik, and Professor Mansour Mustafa for their magnificent lectures, which allow us to update our knowledge about the quantic concepts and their application generally in the quantic devices. The first question for Professor Blatt: can we have in the future, with quantic computer, the possibility of exact resolution of Schrödinger equation without classical approximations for multi-electronic systems? I mean, without separation of nucleus equation and electronic equation. Is it possible by this computer quantic? For Professor Eugene Simon Bolzik, I have two questions. The first is how to balancing between the quantity of light and radiation pressure in order to limit the quantum back action. The second, what's the limit of reduction of uncertainties when we adopt this negative mass approach measurement? Finally, for Professor Mansour Mustafa, what's the cost of these quantic devices can be realizable or profitable? Thank you.
Okay, thank you for this question. So if I understood you right, because I had first the phones up and they was pretty noisy. You were asking, can we have future quantum computers without that solve Schrödinger equations without the classical approximation? Is that correct? Okay, and yes, I think this can be done, but of course there's always approximations at some stage. I mean, you have finite computing powers because of gate operations, so you have a different approximation. You may not need to make a classical approximation. I think the simplest way to see this is the following. Take an analog quantum simulation. The analog quantum simulation, if it can be emulated, as I said, by just embedding things in the right structure of the system at hand, whether that's a lattice system, optical lattice system, superconductors, or whatever you have, and you match the physics, then that can be very well simulated. But of course, there's always experimental errors that you finally have to deal with. If they can be mastered, that's fine. Then you don't have to do any classical approximation. But then, of course, when you write down, say the equations, say for a molecule, you often do a Born-Oppenheimer approximation. So can we do, for example, do calculations on a molecule without Born-Oppenheimer? That remains to be seen how many efforts there are. In principle, yes. In practice, I don't know.
Yes.
So thank you for your questions once again. The first question was how to balance the uncertainty of the measurement with the back action of the measurement, right? And so you think of it in the following way. I make a measurement, I have a meter, which is light, and my uncertainty is comprised of three terms: the noise of light, the signal, and the back action noise. And the ratio of the back action noise to the signal is approximately the same as the ratio of the signal to the shot noise. So if I cancel out the back action, they only have the signal, which is much bigger than the shot noise of light. And this gives me the improved sensitivity by canceling this back action. And could you please repeat the second question? I didn't hear that.
About the limit of reduction of uncertainties when we adopt this negative mass approach measurement.
I'm sorry, a little louder.
I repeat. I ask about the limit of reduction of uncertainties when we adopt this negative mass approach measurement.
So what level of sensitivity we can achieve?
Yes.
Well, it certainly depends. The numbers depend on the actual implementation. But you can put it in the following way. Okay, so let me answer, for example, for the magnetic field measurements. The sensitivity limited by the quantum noise of the spins is essentially 1 over square root of the number of the spins. So you want to have as many spins as possible, provided that you can reach the quantum limit of sensitivity. And in experiments, we demonstrated that we can have 10 to the 12 spins. So 1 over a million will be the standard quantum limit, and we can go beyond that if we generate entanglement. If you generate entanglement of 10 times, then you can go down in this limit by a factor of 10. In practice, in the laboratory, we have achieved the sensitivity of about 1 or a fraction of a femtotesla. And the Earth magnetic field is 10 to minus 4 in Tesla. And we are measuring at the level of 10 to minus 15. So it's really good sensing. Thank you for your questions.
Thank you very much.
Donc, merci professeur Salah pour ta question très intéressante. Sur le coût de la batterie quantique, en principe actuellement, il n'y a que des prototypes. Et on travaille sur la technologie la plus adéquate qu'on peut utiliser pour bâtir une batterie quantique. Actuellement, on fait une petite étude à notre niveau à Casablanca. On cherche c'est quoi la plateforme technologique la plus adéquate qu'il est utilisée pour avoir une bonne estimation coût-prix avec des performances adéquates. Mais la réponse exacte, c'est quoi le coût? Il fallait faire beaucoup de recherches, beaucoup de simulations. Tu vois qu'il y a beaucoup de groupes qui travaillent sur ce domaine, mais un coût précis pour bâtir une batterie quantique, il n'y a pas une valeur précise. Il n'y a que des prototypes actuellement. Les gens actuellement travaillent sur la technologie la plus adéquate qui va nous permettre. Tu vois que, exemple, M. Kouaichel travaille sur les cavités organiques qui ont une super absorption, ce qui va nous permettre d'avoir une meilleure absorption de la lumière, comme ça, une vraie performance de la batterie quantique. Mais un vrai cours de la batterie quantique, ça n'existe pas pour le moment, à ma connaissance. Mais ça demande beaucoup de recherche, des équipes, et beaucoup d'efforts. Mais c'est le futur du storage. La batterie quantique, c'est le futur du storage. Il viendra un jour où on bâtira une vraie batterie quantique et que peut remplacer la batterie à lithium. C'est ma conviction et je ne sais pas si mes chers professeurs partagent avec moi la même idée ou non, je ne sais pas. Mais... Et merci.
Merci, chère Colette, pour vos réponses. Merci, professeur Salah, pour vos questions pertinentes. Je passe tout de suite la parole au professeur Abdelmjid Inan de l'Université Sultan Moulay Ismail de Meknès.
Thank you, Professor Sharqawi. And first of all, I would like to thank Professor Omar Fassi-Fihri, Perpetual Secretary of the Hassan II Academy of Science and Technology. I would like also to thank the director of the whole session, Lala Abtissam Idrissi, Professor Mokhtar Sassi, and Professor Abdelilah Ben Youssef for the invitation. So, starting from yesterday afternoon until now, we have learned more and more on quantum mechanics and statistical physics that we call modern physics. These two thematics will be open for many new applications like quantum computer, and maybe other question will be open, and modern physics that can help to start. So I have three questions for all speakers, and I would like also to thank all eminent professors for their presentation starting from yesterday until now. So for the first speaker in this afternoon, Professor Rainer Platt, told about trapped ion and quantum simulation approaches. My question is in two parts. The first one, what are the advantages of error correcting codes in trapped ion quantum computer, and how do they enhance the reliability of quantum computer? The second part, how do analog and digital quantum simulation using trapped ion provide an advantage over classical simulation? You hearing me? So, for Professor Polzik, he speak about quantum mechanics in the negative mass reference frame, interesting field, and I have learned some paper of you that you have published in physical review later recently. My question in two parts also for you. How does the concept of effective negative mass improve the precision of quantum measurement? And the second one, what are the impacts of this research using negative masses reference frame on gravitational wave detection, and how do this method improve existing techniques? And the last question for Professor Mansour Mustafa, that he présente his talk in French. Donc, je vais poser la question en français. Concernant les techniques, les technologies quantiques et les batteries quantiques, quels sont les principaux avantages des batteries quantiques par rapport aux batteries classiques en termes de stockage et de restitution d'énergie? Et la seconde question, quel rôle jouent les interactions DM et KSEA dans l'optimisation des performances des batteries quantiques? Et je vous remercie.
Thank you again for this. Thank you. Thank you again for this question. And I think it's a very important one. I was not able to talk about quantum error correction in my talk because that would be subject of a completely new talk. Error correction essentially works classically by using redundancy. So when you transfer, say, from one point 0 to the next point, what you do in redundancy, you send packets of 3 zeros, and then the receiver will see 3 zeros, that's fine. 2 zeros, oh, yeah, fine, it's a majority decision. But if there is only 1 zero, then of course it would revert to 1. So that's the classical way. In a quantum way, this redundancy is created via entanglement. And now we have to use error correction not only for the so-called bit flip errors that we get, so that if one spin up goes to 1 0 goes down to 1 and vice versa, but we also have to make sure that we correct for so-called phase errors, that the phase of the Bloch sphere that is maintained. And the latter one is the more sensitive one for trapped ions and for most other implementations as well. So quantum error correction at this time was developed in the 90s by Peter Shaw, by Andy Steen, Calderbank, and a few others. And in principle, Kitaev has contributed a very serious approach. In principle, you need to have a code that makes sure that from the redundant information that is stored, you can get the syndrome, that is, what is wrong in the system and how do I correct for it. And this has to be done in every system. But all the systems that we have are slightly different in their errors that they have, so the different error models. And then the schemes that we have right now all rely on so-called Markovian errors, so there's no memory essentially. But no experiment, and I'm an experimentalist and know from experience, from bad experience, all experiments have somewhere a memory. There's nothing like a non-Markovian noise, like a Markovian noise. It's all non-Markovian. So we have to make an appropriate error model to do these things. Every bit, every implementation, whether that's on atoms, whether that's on ions, whether that's on superconductors and photons, has to make their own error model and then do this. In ions, we still use for error correction the standard error correction procedures, and we are just in the course of adapting this to the specific errors that we have for ions in order to minimize the efforts for us as experimentalists. So that's one thing to do. And for this, we probably need on the order of about, right now we have demonstrated things, all the procedures with a redundancy of 7 qubits, physical qubits for a single logical qubit, plus 2 ancillas, plus a flag, so that would be 10. In order to break even, that's the so-called threshold theorem that we have. So that shows we have to make sure that all of the operations are below, in their fidelity, below a certain, above a certain fidelity. Then we probably need more like 13, maybe 17 ions plus a few ancillas. Right now I'm counting that we will at least need about 20 ions. Some people calculate that for other implementations you need 50 logical qubits. For some superconducting, there are some estimates that go up to 100 or a few hundred qubits. I don't think that this will be viable in the end. If we as experimentalists don't come up with procedures to protect things with a handful of physical qubits, we are doomed. There's no roadblock that forbids me to do that. It's not just a technical challenge, it's also a lot of physics that needs to be done, and there's many groups in the world on the way, and there are really big programs searching for this in order to get this done. For the ions, there's 3-4 teams working on this. We know in Innsbruck pretty well where our errors are, and we are trying to cut them down as much as we can, even to the extent that we go to a different qubit, because a different species of atoms gives you a winning factor of a factor of 2, a factor of 1.5, factor of 3 there. So if you get a factor of 10, we are fine. This is all open, and all other techniques are also struggling with the error correction. Error correction is a real big deal. We can talk about this offline a little later if you really want. I can give you more information. Then the second question that you had, how do analog and digital quantum simulations provide an advantage over classical simulations? This is especially for the things that are very hard to calculate. This is quantum many-body problems, for example. So this is a long-standing problem that we have investigated, also the group of Chris Monroe with ions, but many other teams in the world have done quantum simulations, particularly with cold atoms. There, people have tried to come up with correlation functions that cannot be calculated classically because of the many atoms involved. In our case, up to about 50 ions, we can still do things, but it's already getting hard. We are now at the verge of getting to the point that we cannot calculate things reliably, and we cannot prove things anymore on a classical computer. So that's then the next question that is then asked: how can you verify that the results that we get with the quantum computer are indeed better than the classical computer? This is a very important question, and this is another research project, because we have to make sure that the validation and the verification of quantum computing results is properly done. And there's also a lot of research to be done in this area. But generally, in summary, both analog and digital quantum simulations per se can give you better results, because some problems are simply intractable on classical computers.
So it's my turn now. Thank you very much for the very good questions. And the first question was essentially what we can expect from the quantum enhanced measurements in terms of, for instance, healthcare. Let me put it this way. And the PRL that you probably referred to is where we demonstrated that by using entanglement of the atomic sensor, we can improve the spatial resolution for detecting non-conducting objects. Why is it important? Well, because we are made of non-conducting tissue. And in this method that we call quantum magnetic induction tomography, we demonstrated that we can trace the liquid in, hopefully, your body in the future with the sensitivity which improved by a factor of 4. Is it big or small? Well, there is another method of testing what's wrong in my body, and that is injecting some spin polarized hydrogen and looking for the flow inside the body. This measurement has the time limit of 1 minute. So you only have 1 minute to measure, and if you can use entanglement to improve the sensitivity, then you can make much better measurements in this 1 minute. And the second question concerning the future of the improved gravitational wave detection. Well, my answer is we have done all we could on our budget in the laboratory. People from LIGA and people from the next generation gravitational wave detectors say that they're interested. Well, I will believe them when I have the money on the table. But we hope that it will be of interest for them and also for other measurements beyond the Stank quantum limit, which involve fields or forces. Thank you.
Merci, cher professeur, de vos deux questions très intéressantes. C'est bon? Merci, cher professeur, pour vos deux questions très intéressantes. Concernant la première question, concernant la capacité et les avantages des batteries quantiques par rapport aux batteries classiques. D'abord, les batteries quantiques, ils se basent sur le concept de qubit. Maintenant, la question, c'est pas l'avantage de la batterie quantique, c'est d'abord agencer les qubits, trouver la technologie adéquate et le qubit adéquat, intriquer ces qubits, avoir un nombre assez élevé de qubits pour avoir stocké une quantité d'énergie suffisante qui peut dépasser un peu la capacité stockée par une batterie à lithium. Donc, pour le moment, on n'arrive pas à répondre à cette question. Il fallait d'abord trouver le nombre suffisant de qubits qu'on peut agencer, intriquer. Après, on peut décider la quantité d'énergie qu'on peut stocker dans cette batterie. Maintenant, une autre question qui se pose, c'est la question du taux de chargement. Là, on a prouvé que pour un nombre de qubits intriqués, le taux de charge monté, il est proportionnel de 1 sur n carré. Il est super extensif, 1 sur n carré. Alors que pour n qubits qui ne sont pas intriqués, c'est 1 sur n. Donc tu vois le gain en termes de temps de transfert d'énergie. Donc une batterie quantique, il peut se charger vite et se décharger vite. Maintenant, notre question, c'est question de miniaturisation. Si on arrive à miniaturiser la batterie quantique. Donc, si on a une batterie quantique miniaturisée avec une énergie bien définie qu'il peut donner à des instruments médicaux, avec quelque chose qu'on peut implanter dans le corps humain, donc il y aurait des implications très intéressantes dans le futur par ces batteries quantiques. Sauf que la technologie, il est embryonnaire. Juste, on essaie de mettre en place cette technologie des batteries quantiques. C'est en phase de recherche fondamentale. On essaie juste de comprendre ce que se fait réellement au niveau des batteries quantiques. Maintenant, pour la deuxième question qui concerne le rôle de DM. Apparemment, tu as lu notre article, tu as examiné notre premier article, donc merci beaucoup. Donc, le DM et le KSOA, ça concerne notre premier modèle. C'est le modèle qui se base sur une chaîne avec 2 spins bipolaires qui interagissent via cette interaction bipolaire, plus cette interaction symétrique qui est DM, plus interaction KSOA. Ce qu'on a montré qu'en introduisant ces 2 interactions avec cette intensité, on influence un peu les ressources quantiques, ou bien lorsque je dis ressources, ça veut dire intrication, cohérence, discorde, au-delà de l'intrication, tout ces valeurs qui régissent un peu l'intrication. Donc, en influençant ces ressources quantiques qui régissent un peu l'interaction entre les 2 qubits ou les 2 spins, on peut influencer les performances de la batterie quantique. Et on a pu avoir que l'ergotropie, le travail qu'on peut extraire, la capacité de la batterie, elle dépend de ces paramètres. Donc, si on arrive à avoir un ensemble de 2 qubits avec des paramètres bien définis, adéquats, qu'on peut réaliser expérimentalement, on aura une batterie quantique avec des performances trop élevées. Donc, mais ça reste purement théorique, parce qu'on n'a pas fait d'expérience sur un système dipolaire. On a juste simulé un peu le calcul, et on a trouvé qu'en influençant, en agissant un peu sur ces paramètres, on peut influencer les performances de la batterie quantique. Et ça, par la suite, si on arrive à faire ça expérimentalement, donc en ajustant un peu ces paramètres, on peut influencer les performances de la batterie quantique. Et merci, cher professeur.
Merci, chers collègues, pour vos réponses très précises et pour les questions intéressantes du professeur Aynen. Je passe tout de suite la parole au professeur Mohamed Bennaï de l'Université Hassan II de Casablanca. Professeur, vous avez la parole.
Merci, Madame Charqaoui. Donc, je tiens tout d'abord à remercier les instances de l'Académie des sciences pour l'invitation. Donc, je suis très content d'être parmi vous aujourd'hui. En parlant de la technologie quantique, bien sûr, je voulais juste signaler qu'on parle beaucoup de la seconde révolution de la théorie quantique. Et c'est ça ce qui est bien sûr, qui est important, parce que si on parle beaucoup de technologie quantique, parce que cette révolution, elle est accompagnée surtout par des avancées expérimentales. Ça, c'est un premier point que je voulais signaler. Donc, c'était le premier point. Et puis, le deuxième point, c'est qu'on a réalisé, lorsqu'on parle par exemple de qubits, par exemple, on a réalisé ces qubits-là expérimentalement. Ça, c'est très important. Et le deuxième point, c'est cette course vers les technologies, ces nouvelles technologies quantiques. On signale que, bien sûr, on a pris des décisions à très haut niveau des États-Unis, en Europe, en Russie et en Chine. C'était ça en 2019, pour bien sûr lancer des recherches et financer des recherches avec des sommes colossales, bien sûr, sur ces nouvelles technologies quantiques. Il y a aussi cette course dont on a parlé des grandes firmes telles que Microsoft, IBM et Google, bien sûr, à la recherche de cette ordination quantique. Voilà, donc ça, c'était juste une remarque que je voulais signaler dès le début, parce que actuellement, on ne fait pas seulement le centenaire de la mécanique quantique, mais aussi on est en train de vivre depuis un certain nombre d'années, cette seconde révolution, ce qu'on appelle cette seconde révolution de la théorie quantique. Ça, c'est un premier point. Pour finir, juste une question pour M. Mansour. Lorsqu'on parle de batteries supraconducteurs, nous savons que on a déjà réalisé des qubits supraconducteurs, par exemple la base de jonction Josephson, par exemple. Et je n'ai pas beaucoup compris pourquoi on n'a pas encore pu réaliser ces batteries supraconducteurs. Merci beaucoup. Merci, madame.
Merci, cher professeur, de ta question. En principe, pour ce modèle de batterie quantique qui est basé sur les qubits supraconducteurs, donc on vient de proposer ce modèle, on vient de soumettre ce papier. Donc, à notre connaissance, on ne sait pas s'il existe une vraie batterie quantique qui se base sur ces qubits. C'est vrai, le qubit supraconducteur, c'est un qubit mature, il existe déjà sur le terrain, mais le concept de batterie quantique basé sur ces deux qubits supraconducteurs liés par Hamiltonien, ce n'est pas encore fait, à ma connaissance. Donc, je ne sais pas, mais c'est le modèle le plus apte à réaliser, donc, puisque le qubit supraconducteur il existe déjà. Donc, et d'ailleurs, nous, dans cet article, on propose une méthode de réalisation de cette batterie quantique qui se base sur ce qubit supraconducteur. Et merci, cher professeur.
Merci pour cette réponse et on espère que peut-être que le Maroc sera le pionnier pour cette batterie, nouvelle génération, on verra bien. Alors, je passe tout de suite la parole au professeur Abdelouhad Hjaji de l'Université Chouaib de Khalid El Jadida. Professeur, vous avez la parole.
Merci. Merci. Je tiens tout d'abord à remercier les organisateurs de cet événement très riche, très intéressant, et je suis très heureux d'être parmi vous aujourd'hui. Donc, ma première question, ça sera pour Monsieur Polzik. La mécanique quantique dans un référentiel de masse négative est un sujet très important et très intéressant qui touche des concepts théoriques avancés et aussi en fait des recherches dans la physique fondamentale. Bien sûr, la masse négative est une hypothétique forme de matière où la masse serait opposée à celle des objets ordinaires. Ce concept, si on comprend bien, ce concept pourrait donner des résultats surprenants pour la mécanique quantique et aussi la relativité et aussi la cosmologie. Et une première question concernant la masse négative. Quel rôle la masse négative pourrait-elle jouer dans l'influence de la courbure de l'espace-temps selon la réalité générale? Et aussi, la masse négative pourrait-elle jouer, expliquer certains mystères non résolus jusqu'à maintenant, comme la symétrie matière-antimatière ou la nature de la matière noire? Ça, c'est pour M. Polzik. Il y a une deuxième question pour M. Mansour concernant les batteries. En fait, vous avez expliqué tout à l'heure sur les batteries quantiques. Nous aurons peut-être quelques questions concernant en fait le temps de chargement, de déchargement et aussi la capacité comparée aux batteries classiques en fait qu'on utilise naturellement. Une troisième question, et je m'excuse en fait, c'était donc mais d'ordre général en fait pour les ordinateurs quantiques, pour M. Blad. Une question pour tout ce qui est en fait ordinateur en fait quantique. Si on parle d'ordre général, quels sont les obstacles qu'on peut avoir en utilisant en fait tout ce qui est en fait théorie, les obstacles majeurs qu'on peut surmonter pour créer des ordinateurs quantiques puissants et accessibles et qu'on peut interagir avec les ordinateurs classiques dans l'avenir proche. Et merci.
Thank you very much for your interest in my talk and to this interesting question. I have to say that my first answer to your question is I don't know. But maybe the next question would be, the next level of answer would be, how can we use this principle, for example, to evaluate the curvature of space-time and so on? If we can use this principle to detect gravitational waves in a better way, then this will be the window to studying gravity and so on. Another related question is that if we are able to entangle more and more massive objects and put them in larger and larger superpositions, then we can test the limits of quantum mechanics along those directions. And in our experiments, according to some estimates, the combination of the mass and the uncertainty that we are measuring is actually one of the best for all kinds of measurements. So that's our hope. Thank you.
Merci, cher professeur. Donc, merci pour ces questions très intéressantes aussi. Donc, concernant la capacité, comme j'ai expliqué auparavant, donc, si on veut vraiment différencier la capacité d'une batterie quantique avec une batterie classique, il faut avoir une taille égale. Maintenant, question batterie quantique, il faut d'abord pouvoir agencer les qubits. Il faut avoir un nombre élevé de qubits. Chaque qubit, il va stocker une quantité d'énergie. Et il faut sommer le tout. Donc, c'est difficile de faire une comparaison en termes d'énergie ou de capacité de deux batteries, alors que là, on travaille de quelques qubits, et là, vous avez des grandes batteries. C'est pour le cas de stockage, mais ça reste, le stockage, c'est juste la différence entre un état excité et un état fondamental. L'écart d'énergie, c'est l'énergie qu'une batterie quantique stockée. Et une batterie quantique, elle peut être modélisée par un système quantique 2 niveaux, 3 niveaux, 2 niveaux, donc c'est pas... c'est juste un système quantique. Maintenant, la question... qui est très intéressante, c'est le temps de chargement. Là, le temps de chargement, il a été vérifié qu'on peut gagner en termes de temps de chargement. Si on a des qubits intriqués, le taux de chargement il est proportionnel à 1 sur n carré pour un qubit, alors que le taux de chargement pour des qubits non intriqués, c'est 1 sur n. Donc, si vous avez des qubits, alors le taux de chargement 1 sur 100. S'ils ne sont pas intriqués, 1 sur 10. Donc, vous gagnez beaucoup en termes de chargement, en termes de transfert d'énergie, en termes de la quantité d'énergie que vous pouvez transférer à votre batterie, soit en processus de chargement, soit en processus de déchargement. Question de stockage, il faut comparer des batteries à volume égal. Et là, on est juste sur des prototypes. L'exemple de James Quaish, elle travaille juste de cavités organiques avec un phénomène de superabsorption. Donc, on peut absorber la lumière d'une manière très spécifique et qui dépasse de loin un peu le taux de chargement des batteries classiques. Et merci pour votre question.
Merci.
Thank you again for the question. If I understood this right, this is a very noisy channel that I have here. You were asking about the hassle, how to use a quantum computer, and how are they then accessible to a large majority students and scholars alike. Now that is certainly true for the last, say, 10, 15 years. These are experimental devices. IBM was the first company who put their quantum computers at the cloud service, so they're very accessible for everybody who signed up. It was initially not that easy, but it's getting easier and easier. Right now, we have a de facto standard. A Qiskit is already mentioned, is a computing tool that has been introduced by IBM as open source and can be used by everybody. There are other dialects like Circ, like Pennyline, there's a few other languages around, but 90% of what currently is being used by users for quantum computers is Qiskit. And if you want to use it, I would suggest that you really try to get access to one of the IBM machines. They are not all expensive, some of them are there for free. Also, our company, AQT, has one machine online on the cloud, and it's made available for scientific purposes and also for teaching. And there are many others. So that is doable. It's getting better all the time because we have to supply these systems. Concerning your second question, this is precisely what the current efforts are about in Europe, but also so in other areas like in Australia and in the US. We already have sold, and so do the US and the IBM companies, quantum computers to supercomputer centers. The idea is not so much at this time to really be competitive with supercomputers, but for them to learn how to use them and how to incorporate them for specific problems that are done at supercomputers. And specifically, for example, in Munich, for example, the so-called Leibniz Supercomputing Center, they have developed in the Munich Quantum Valley over the last 3 years a specific software that's called the Munich Software Stack, which is accessible, also not quite open source, but it's openly accessible, and you can use it, and it's a de facto standard in the area. So I think this is being programmed as an API, as user interfaces that you can access. It makes your life easier. And if you want to teach students or classes, and you want to get them access to quantum computers, I think this can be organized. Let us know, and I think this is something that we always encourage. And so interacting with classical computers in the near future is exactly the point that is being pursued by the supercomputing centers, because it needs the interface on one hand, but also it needs, in order to get really fast, once we have enough hardware, quantum hardware available, it needs to be accessed fast in order to make use of that speed. Otherwise it's of no use if there's a bottleneck.
Thank you, dear colleague, for your response. Je remercie les conférenciers pour leur présentation et la réponse aux questions très intéressantes. Je remercie aussi les collègues pour leurs questions pertinentes. Et ces discussions nous a permis de voir que dans divers domaines, il y a des avancées récentes et des avancées futures, des technologies quantiques. Et c'est comme si on a ouvert une porte, et espérons qu'on ira bien plus loin. Merci encore. On arrête la session.
Merci, chers collègues, professeur Sharkawi, pour la modération de cette session. Donc, ainsi se conclut cette 3e session de cette 2e journée. Et pour ce fait, je tiens à remercier chaleureusement tous les conférenciers de cette journée, de ces 3 séances d'ailleurs. Je tiens également à remercier tous les intervenants et les collègues des différentes universités marocaines d'avoir entamé une discussion riche et un échange mutuel avec nos différents conférenciers. Je remercie également les différents modérateurs et les différents rapporteurs des séances de discussion. Et donc, on continuera bien sûr demain avec une nouvelle journée, qui sera d'ailleurs la dernière journée de cette 18e session plénière solennelle de l'Académie Hassan II des sciences et techniques. Il sera aussi riche que ces 2 premières journées, mais sera aussi, je répète, la dernière journée. Donc, on se rencontrera effectivement demain dans cette salle à partir de 9h. Et d'ici là, je vous souhaite une excellente soirée, mais il y a une annonce importante qui sera faite par professeur Houmed. Merci à tous et à demain.
Je disais aux collègues ici à l'hôtel qu'un transport partira à 19h15 directement de l'hôtel. Les collègues ont reçu des invitations, ils sont dans leur cartable.